હેલો. અવાજ ચેક કર યુટ્યુબ પર. અવાજ આવે છે? અવાજ આવે છે યુટ્યુબમાં? આવશે. હા, ડીલે છે.
આવ્યો આવ્યો.
હવે એક વસ્તુ, જેવું જ યાદ રાખજે, ખાસ કરીને જેવું આ છે ને સ્ટાર્ટ થઈ જાય, બરાબર, પોસ્ટર શેરિંગ કાઢી નાખવાનું છે. અહીંથી શેરિંગ, પોસ્ટર શેરિંગ કાઢી નાખવાનું અહીંથી. કારણ કે અહીંયા આગળ જે પ્રેઝન્ટ કરતા હશે ને એનું જ રાખવાનું, ભલે અહીંયા આગળ પછી એનો ફોટો દેખાય. સમજો? કાલે જે ભૂલ કરી યાદ નહીં કરવાની. કારણ કે એમાં થાય છે કે વિડીયોમાં પછી શું કે શેરનો પેલા શેર કરીએ ને એટલે આ નાનો જ ફોટો જાય છે પેલા ઝૂમમાંથી, નાનું જ ટેપ જાય. એકચ્યુઅલી કેમેરો ફોકસ અહીંયા આવવો જોઈએ એનો. હે? એ પીપીટી કોઈ સાંઈ દેખાય જ નહીં લા. હા, એ તો શેરિંગ વખતે તો પીપીટી શેર કરવાની જ નહીં યાર, એ તો સીધી વસ્તુ છે ને. પણ જ્યારે કોઈ બોલતો હોય ત્યારની વાત કરું. જ્યારે કોઈ અહીં કશું શેરિંગ ના કરેલું હોય ને, સમજ? બસ. એટલે કશું અહીંયા આગળ કશું હોય નહીં ને, બસ એનું એનું આખું આવવું જોઈએ. સમજી ગયો? એટલે પોસ્ટરના ચક્કરની અંદર ને આપણે પેલું કંઈક લોચું ના પડે એટલું ખાસ ધ્યાન રાખજે. બરાબર? હા, કાલ વાળો જશે ને લા. ડન. પણ એ શું કરે છે? આપણે લેપટોપ લઈએ ને એચપી વાળું.
इधर ली नया बोतल डाल दिया ये आपने बोला नहीं ना देखने के लिए ऐसे
अब हो गया पता पीछे से लेने से. સાઉન્ડ નહીં આવતો સાઉન્ડ.
Our lightweight and performance is one of the automotive uses in many applications, reducing vehicle mass and boosting driving experience. We help designers build high-end performance and luxury cars. With new processes and methods, we're cost-effective, fast, easier to manufacture, combined with other materials. We equip electric cars and hydrogen fuel vehicles while preparing for the future needs of transport. In aerospace, we save fuel with our lightweight. Today, we total over half of the mass of commercial carrier. We can provide engine parts. Our advanced composite fuselage improves aircraft performance, safety, and reliability. Play a central role in current and future innovation programs. Powerful rockets to future we inspire construction engineers and architects. They provide resistance, insulation capacity, and design flexibility. We reinforce critical bridges. Our bridge decks carry heavier traffic loads. Unleashes creativity and rapid.
પછી તો સાંભળ આ કેમ નાનું આવે છે
શેરિંગ અહીંયાથી બંધ છે.
શેરિંગ બંધ કરી ને
એક મિનિટ યુટ્યુબમાં જોવાનું આપણે યુટ્યુબમાં ફૂલ
Good morning. So I, Hemant Chauhan, on behalf of CECA Asia and Ahmedabad University, welcome you all to the Day 2 of Composite Industries National Conference and Exhibition 2024. Yesterday, we had a large number of highly fruitful and enriching experiences being shared by the eminent speakers, and today, the journey will continue and will have lot many areas to be covered. The different domains of composites covered by different experts from the different domains of the global applications of composites will be taken up. And in that series, without taking much of your time, I would like to introduce Mr. Nitin Sharma and Mr. Prashant Kumar from SAC ISRO Ahmedabad. They will be presenting their works in the domain of role of composite materials in space-borne payloads. So, may I request Mr. Nitin and Mr. Prashant?
Okay. Yeah. Good morning to all of you. My name is Prashant Kumar. I am from Sai Kisro, Ahmedabad. Mr. Nitin Sharma, he is on official tour, so he is not present today here for during this talk. So on behalf of Mr. Sharma and on my personal behalf, I would like to thank organizers for giving us this opportunity to share some of our thoughts regarding the composite material processing application, especially for the tricky customer, what we have, that is space. Space itself is a very unique thing, because everywhere, if there is a space, so someone would like to occupy. But occupancy should be with the greater achievements and with the significant goals. So the topic what we have been given, that is the role of composite material in space-borne payloads. Here three specific words we have, that is a space itself, composites, payloads, and the role. When the role comes, there is a responsibility also. We have the payload. What payload does for us, it carries our ambitions, it carries our purpose in space to fulfill our goals, what we have dreamed for the mankind and society. So in this spirit, I would like to continue my presentation. Okay. So this outline of my presentation is the introduction, composites and its classifications, composites in space, one payload, especially we will discuss in detail, basic design approach for composite, how to, okay, I will not go much in details, but okay, we will touch upon. Manufacturing and characteristic of composite for the space applications, and the scope of the research for the future, what we have desired and what we are looking for from the academia, industries, and our research organization also. So, the Indian satellite system, if you see, we have the variety of satellite for the various purposes, especially for the communication, for the telecommunication, direct to home services, telemedicine, teleeducation, meteorological observation, disaster management, radio networking, and okay, this rescue operations, remote sensing, and scientific studies, just like our Mars mission, Chandrayaan, and so forth. So this is a satellite system. Okay, these are the classifications what we have made, what type of satellites we are aiming. I have already explained that communication satellite and Earth observation satellites, small satellites basically for the some identified or some specific purposes. Scientific experiments like Chandrayaan, I already mentioned Chandrayaan, Moon mission, Mars mission, and recently we have launched for the Aditya mission for the solar exploration. And experimental satellite, just like SR yesterday it was talked, how the experimental satellite re-entry experiment was done from ISRO to take the object or to take the satellite from or the spacecraft from the outer space to the our inner and ground. So this is the way satellite communication happens. There is satellite. It is around in the orbit in the Earth, and how there are ground stations. There are the equipments required to make the communications, and you can see there is a two-way communication. It has to be started. Definitely, all communication need to be passed through gateway. Gateway is where our main systems are there, and then definitely our users. This is the way they communicate, and this is the way our whole system works and establish the communication between the user and between the service providers. So, taking this into our account, how the composite materials and how this specific kind of approaches will help us to minimize the weight or the mass weight to launch the spacecraft in the orbit, so that we can get the maximum advantage of the cost per se as well as for our the life also. So composite already it is there. What we have mentioned, that two or more materials combined on a microscopic level. We are not going for the microscopic analysis because that will need some other classification also. But micro level, which means the two or three, maybe three also, this constituent will be bonded together with the help of some identified processes to get a unique material. That the property of that material will be differently from all the other constituents. And they usually exhibit the best qualities, their constituents, and other some qualities neither constituent process. Just like that, we are having that resin, fiber, some other things, but they don't have, they don't possess the kind of compressive strength. But if they bonded together and they have got that kind of property after the processing, they can exhibit this kind of property also. So the uniqueness of the material. Definitely one is reinforcement. We say that fibers or any kind of that, those who are the main load-bearing members, they have been called as reinforcement. Another is definitely matrix. They will bond together, they will protect the reinforced material from the other outer space or the other environmental conditions also. And matrices that is there. So what composite offers us, to why we have to go for that, and what kind of these advantages we can take in our structures. So you can see this is a high specific strength, we say, with respect to density especially. So strength the only will not matter here, because we have to have lighter sense also, how it can be, the mass can be reduced. So in that scenario, we have put high sense, specific strength and high specific modulus. Both are required for the purposes of our space. And the action strength, because we have mentioned to, because this will add on the tailoring of this material, so that we can get the desired property for the specific purposes. Corrosion resistance is there. Stability, why we say the dimension stability is very much essential. Yesterday, one thought was there that a kind of optical payloads we have, their dimensional stability very much essential. We are having very much accuracy requirement there for the performance purpose. So that CT will matter here, coefficient of thermal expansion will matter a lot. Not only CT, here the coefficient of moisture absorption also will matter, because in space definitely moisture will not be there. So kind of property we need here, they should be very much means competent with that environment also. So that ACM will also matter there. And okay, radar transmission effectivity is also required, because some kind of protection we have to protect our equipment, so that we used to say that is like red dome or some kind of cover is there. So that should be transparent in that one. And magnet, non-magnet is also one important criteria you can have. High impact distance is there. Maintenance cost is low, because we don't have a differential material bonding and all these things we can avoid in different class of adhesive other things, so that we can go for this maintenance. Lamp penetrability, the part consolidation is also there. Small to large part geometry is possible, because we can have different kind of toolings and our methodology for the curing and all these things, so that we can tackle this problem also. And tailored surface is okay. Design flexibility is there. With the help of various tools and our processes, we can choose this also. So if you see that spaceborne payload components basically required, majorly I have classified in three domains. That is the first, to meet the structural requirement, second to meet the thermal requirement, and to meet the functional requirement. These are three basic classifications. The detailing is also there, but I have just qualified in these three. So once we call the structural requirements, so definitely high specific strength and stiffness. I mentioned strength and stiffness is required to meet because we have to launch the spacecraft into space. So various components are there. They have been assembled together. So there some specific requirement for the environmental conditions are required. Just like the frequency is there. So they should not be in coupled mode. So that if they are coupled, then definitely the resonance can happen. The structure can have some kind of damage or performance degradation. Strength is also in same scenario, that can help us in designing with the safer margins of the requirement for the specific product as well as total stress. if you see the thermal requirement, definitely low CT and high thermal conductivity is required, because definitely their environment is there. So many components or many products, what is used in the spacecraft or in satellite, they need some kind of stability in temperature, because otherwise they will not function. So that conductivity will help us to for the thermal management or heat management, so that their functionality can be sustained. As well as the low CT coefficient thermal expression I mentioned already, study it was discussed, so that the dimensional accuracy is one aspect, as well as when they have been initially they have been there, so that their effect cannot be translated or cannot be reflected in other equipment also, so their performance and these performance can also be established. So CT will matter a lot, especially for the large hardware like camera structure and other things. There, this will affect largely. And high electrical conductivity to meet the functional requirement. We are launching some kind of in many satellites where there are reflectors and other equipments where the functionality is one aspect. Functionality means that our waves or our microwaves or they have to be traveled in the some component there, the reflect this one electrical conductivity is essential. Without that they will not function. So that requirement is there, so that if the composite can have that kind of a property, definitely the reflectivity point of view for reflectors up to some certain band of the this one frequency we can use directly CT, because CT offers some kind of property that can be used. But for the higher band of application, definitely some kind of surface improvement is required, where the reflectivity can be improved, electrical conductivity also will be improved, so that they can be used in that scenario, like some kind of metallization or some kind of cladding or something we can do to meet these things. Though these three will guide us to how to select the material and how to select for the specific applications. So again, similarly we have just, you can see that how the ceramic metals and polymers we have just taken, how these three can be chosen, so that we can go for the selection of the material for our specific identified product and purposes. So lightweighting, the low density, design flexibility, already we have mentioned these things. But overall composite are highly valued in space industries for their lightweight, high strength, thermal stability and other valuable properties. Their use enables the development of more efficient and capable spacecraft and launch vehicles. Launch vehicle also we are using composite in large amount, and leading to advancement in the space exploration for satellite development also. So definitely, nutshell what we want to convey that composites with the specific other properties and with the selectiveness of this material for the stages of the vehicles as well as spacecraft can offer such very good amount advantages in the our weight saving as well as our payload life also. So that is already classified. Composite reinforcement matrices, metal matrix, ceramic, carbon matrix, and polymer in thermoplastic and thermostatic. Also we have some discussion on, but especially in space we are mostly using our thermosets, because the space the property should not be changed with the environmental conditions. Again, that classification we have put metal matrix, composite, ceramics, and polymer matrix. That our reinforcement, this class of the reinforcement are required, and metals and polymers and ceramics, this kind of matrices we can use for different kind of product development, namely that PMC and CMC and this MMC. So a type of reinforcement we have mentioned here, that we are using unidirectional fibers, some kind of continuous fiber, some kind of this soft fibers, biaxial this one fabrics can be used for the different purposes, and they can be tailored for the multi-axial what we have explained there. And random fiber also, because if you want some kind of isotopic property, so we can choose random fibers and they can be mixed with resin and cured for the applications. And the knitting is also there in because the fibers can be knit together in differential axes, so that the properties can be taken, the advantage of the fiber properties can be taken in the particular direction. One specific application means process is braiding. Braiding, there you can see that the three axes yarns can be placed in a single plane, we say. There the different axis fibers can be put, and then we can take the advantage of the axial as well as this one braided direction fiber. because definitely that fiber only will exhibit the property that only we can utilize. So that will give the advantage in the particular direction in a single plane. So configuration wise, we have given that we have standard here, that fiber reinforcement composites, particle composite, clay composites, laminated composites, sandwich composite, and combined composites means we can have both kind of combinations so that we can tailor some kind of requirement. That also we have done here. Okay, this is again. So now we'll come to the space structures. So we see that we have the in space what we are launching. So that we have launch vehicle or rocket, what we say, spacecraft or satellite, payload transponder, antenna, camera, etc. These are the main three domain where we are dealing in our space this program. So if you see the launch vehicle, this is a 3-stage vehicle. This is a GSLV Mark 3, the third generation launch vehicle. So if you see, that is a 3 stages. We have the basically in our lower stage, that is our motor, that is our means motor cases and some kind of propulsion stages are there. And second stage also definitely cryo stage, that is also for propulsion purpose. And the last stage, that is our payload, where the payload and other scientific instruments are there. So if you see that each and every stage that composites are there, I have mainly classified. Just kind of you see that this strap-on nozzles are there. There is a boosters is there. So booster also motor cases are there. That also high amount of composites are essential to reduce the masses. Second stage also composites are required for just like propulsion tank, propellant tank, pressure tank, where that we can use. Spacecraft also many space. I will come to the next slide where the space satellite spacecraft we are using that composite material. But mainly if you see the stage wise, if you reduce the mass, how much advantage we are getting in the payload, that will determine the selection of the material. I was mentioning the selection, how to select it. We cannot use everywhere composite in space because that will have their own benefits and this one. So what we see, if we go for the first stage, reduction of the mass, advantage of the higher stage or the final stage is 1/4 terminology, if you say. Second stage 1 by 3, third stage 1/4, and the final stage total. So 1 kg mass is saved in this one, only 0.25 kg mass will be added in the payload. So we have to choose judiciously that where the reduction is required. So what we do, we say that third stage and fourth stage maximum amount of the composite we wanted to use, so that we can get the direct advantage in the payload. Payload mass saving will definitely lower the cost of launching, as well as it will improve the life of the spacecraft satellite. So that advantage we have to take. So that's why we are choosing here. And you see the equipment in the third stage and fourth stage, equipment routes are there, payload fairing, the 5-meter payload fairing is there. So a very huge amount of mass saving is there in that stage also. That will directly benefit our payload, payload gain. And liquid stage and other stage, because of specific application where that high temperature and other things required, there we are using a composite in lower stage also. So it's not only the essential, we can use third or fourth stage also, where the requirement and the application is essential, we are using. And if you see spacecraft or satellite, where we can go for the composite especially, if you see the reflectors, we have the waveguides, we have the feed horns, we have brackets, we have other this one essential parts with the spacecraft required. So I will go for these three basically. If you see one kind of this one feed bracket was there, one feed horn was shown. That's the horn was there, liner, one aluminum liner we have placed. Why we have placed the liner? Because that is the requirement for our functionality purpose. That was only because if you can meet the requirement with this kind of composite material itself, so we need not to go for the metallization and other thing. So this is the one challenge where the material can have the kind of reflectivity or kind of electrical properties, so that they can be chosen. This is very huge amount of this one feeds and other waveguides are required for the space, our payloads, so that if there we can have that improved property, definitely a lot of thing can be changed and very huge amount of mass can be saved. Secondly, that this one, our reflector also I mentioned, so specific and applications just like KU band and below. We can go for directly this CFRP, but if you want to go for higher version, K, Ka and above, so definitely that functionality of the reflector to be improved, especially for the electrical properties. So there the coating or some kind of metallization essential for the surface. We are doing here some coating we are doing and some kind of cladding we are doing. But what we wanted that definitely these two processes are adding. So that can be reduced here, and then if the material itself can exhibit the property, we can go for the directly for the composite itself. And these are the parts in various kind of satellite, like our Earth observation satellite or optical satellite, as well communication satellite. Many parts we have shown, like our antennas are there, some kind of means solar panels are there, some main structure there, propellant tanks. The propellant tank also there is a composite, because that you can see the inside that propellant tank, the huge size tankage are required. That we are going for the metallic, because definitely we have to store at high temperature, pressure, so that permeability of the material is one aspect. So we can have the, if you go for the some kind of material, those can take that property, that requirement. So very huge amount of mass saving can be done, because they are the main mass. Okay. So composite material in satellite, what we see, I have just, these are the realized hardware we have taken from the internet. If you can see here, this is the mainframe structure. So this is structure where all the satellite component will be assembled around this hardware. So that you see this kind of huge structure we are going for the composite, because you have to save the mass. And we have to take the advantage of the tailorability other things, so that this requirement in this space can be met. If this is a I3K, I4K, I6K class of satellite is there, where that size, shape and size will be enhancing, so that in the similar ratio we can save the masses also. So you can see the usage of composite material in the mainframe structures. Here you can see that reflectors already I have mentioned. That reflector also we are in large amount of composite materials are being utilized. Thirdly, you can see the pressure tank, that is pressure or propellant tank we are using. Here also that we are storing gases at very, very high pressure, so that they can be utilized in the space for propulsion purposes. But you can see here that is a filament winding process is there, where that inside one liner is there. That is a very thin liner is there. Over that this reinforcement is being overlaid for the purposes. What here advantage we can take from the composite, we can have that kind of material, though the liner can be extracted, so that mass of the metal can be reduced. That one aspect, already I mentioned in propellant tank, very huge amount of mass saving is there. Okay, how the structures we have evolved in space purposes, just like this, our monocoque structure are there, semi-stiffened structure are there, corrugate structure are there, and honeycomb sandwich cells are there. So these are the classification, and with the various purposes we are choosing based on requirement. Just like that for you, if you see this kind of hat station structure where the compressive loads are there. I mentioned the third stage or in that third or fourth stage of the spacecraft, where the payload raptors are there and the equipment bay is there. Their compressive loads are very high in the requirement. There we can use this kind of station structure. And where that only stiffness and other requirements are there, we can go for the honeycomb, this one, cell purposes, sandwich cell also. So we have to choose based on the requirement, this kind of structural configuration with the composite to save the mass and to fulfill our purpose. Okay. So space structure already, because we have come to the structure part. So there is a we have to provide the platform to support the kind of equipment or kind of the payload we have to carry there. Integrity purpose we have to get together for the final satellite purposes. And mechanical load bearing, definitely that component will be loaded and they will be subjected in the different environment. For that purpose also we have requirement. Electrical and thermal conductivity path also we have to provide for the this one. Primary structure, secondary structure and tertiary structure we have classified in 3 domains, where that the primary structure they are main load bearing members. They should not affect anything on secondary or tertiary hardwares, so that they have the, just like you have seen the mainframe structure, they are the primary for the spacecraft. So their choosing of material with the strength, with the modulus purposes is essential here. Secondary structure basically to decouple with the primary structure, so that only stiffness and some kind of strength requirement is there. So we can choose in between what kind of material we have to select and what kind of configuration we have to go for the structures. And tertiary definitely they have been only for our purposes, functional purposes we are going. Definitely the requirement is there, but that is not in line with the primary and secondary. So once we are going for the monocoque told and had a different structure we have told. But third was the sandwich structure. Sandwich structures are mostly used in the spacecraft structure because they can be utilized basically for their bending property. Other thing they can help us for selection of this material to get the stiffness as well as load bearing capability also. And you can see this kind of cores and this kind of rigid core, flex core, or overextended core, corrugated core. These three type of cores are required for selection of shape. And just like that, if you have the reflector, so we can not go for the rigid core, we can go only for the flex core. So this kind of core selection is essential to get the desired property of this different structure or sandwich structure. So how the core is manufactured, that also is explained here. You can see that that is a hop is there. You can see the hop, they can cut and they can be expanded. So there is a process is there, and second process is corrugated core. So they can be stacked together and then can be sliced. The two methods is there. Basically, we are going for the first one, expanded one, and you can see that last one is the flex core. The flex core, you can see the cell configuration. They can, because this configuration they can take they can take the shape of that our mold or what kind of a tool is there for the required purpose. So, category of advanced composite we have categorized in these three, basically four main parts. The structural composite, filament bound composite, ablative composite, thermostructural composites. Structural parts, I mentioned that sandwich, corrugated structures, and as well as this artificial different structure are there. Filament bound basically used for the kind of pressure washer motor cases where that axisymmetric object, this product can be bounded and can be used for the application. Ablative where the high thermal heat or other thing is required, they are ablative using. Thermostructural component where both can be together, just like in our camera structure where our dimension stability as well as our this one structural requirement there both we can select for the application. So we are basically going for the structural sandwich and filament bound, and this one for the monocoque for the this one thermostructural composites. Okay, the feature of composite manufacturing process, the material and the products made in single operation that because we are going together. The manufacturing process not only involves physical changes of the consequent but also at the chemical reaction at the time of processing. The process must ensure completion of chemical reaction, physical changes, and creation of correct material and structure. No physical or chemical damage to the fiber due to the process temperature and pressure because that also will come in next one. No wax, blister or cracks in the matrix and no fiber breakage. In metal, the in-orbit properties cannot be changed during the fabrication of the structure. However, the composite material is formed at the same time as the product or component or structure is being fabricated. It means that the process plays a vital role of determining the performance of this resulting structure. So, steps involved in manufacturing of composite is pre-processing, processing, and post-processing. So, these three stages we can determine. Or we can have that how the material can be pre-processed and post-processed, and after the post-processing we can have the material for the use. If you can see the pre-processing, that we can have the layup, we can have the pre-peg, or we can have the different kind of material what to be taken for the curing. So in the curing we can select the process. Here what we have taken, that is out of autoclave curing is there, that like this one molding and curing is there. So in that we have to go for the mold in the vacuum bag condition for the curing, and this kind of cycle or this is we have taken for some specific thing, but we can have a different kind of matrices for and accordingly that we can choose the cycle. So composite layup technique, you can see that wet layup or hand layup is there, vacuum bag molding is there, autoclave molding is there, filament binding already is there, pull through resin transfer molding is there, reaction of sandwich composite is there, press molding is there, and autoclave molding and tape binding. These kind of processes we are using for the reaction of product for the differential purposes. So this is the hand layup. You can see that there is a mold, there is a kind of this our wet rag is there. They can be laid in the desired orientation, and you can see the shaping, and they can be put together, and they can be consolidated, and then we can apply the heat for the curing. This is the vacuum bag molding is there. In the vacuum bag molding, that mold is there, and over that our composite laminate or stacking we can do, and we can have the vent housing also, vacuum where that we can take the outgassing outside the after during the curing also, and they can be cured together, and we can get the desired product. You can see the curing cycle is there, and at what stage we have to stop and what stage we have to cure, and we have to release the vacuum so that the final product can be get without any distortion. So this is the cycle we have to use for the vacuum bagging curing. This is the procedure we are following for that. There is a various this one consumables are there like vacuum bagging films, release film, other things are there. So these can be taken, and then this product can be realized. So in the extension of this one, this is autoclave molding in there. Autoclave molding, it is similar to the vacuum bag curing. Only thing that inside also some kind of additional pressure we can apply, so that the compaction can be improved and the better property extraction can be achieved for the material is being used. This is the curing cycle for the autoclave. There the pressure and other thing has to be synchronized together so that the property or the this material can be cured in a required manner. So you can see where the pressure is there and where the vacuum we can apply and we can reduce, so that the product can be cured properly in this autoclave. And this is the filament mount. Filament mount also, this is uniqueness of the process is there. This is a CNC based process, so totally automated one. And here the only thing is there that we are dealing with the fiber directly, so that the fiber placement over the mandrel, you can see the mandrel. That mandrel is a cylinder dome tank is there. The cylinder and this dome together have been bonded, so that we can enlarge that means our shape of the this one tank. Only thing is what we uniqueness in this process is that you can see the fiber we are dealing directly, so that we can utilize this maximum property of the fiber here. Otherwise, everywhere we are manually placing the fiber, so definitely that some kind of error in the placement of the fiber is happening, and we are not getting that kind of maximum property out of the material. But this is the process we can get. But limitation is this process is there. We can have only like axis symmetric object we can bond. Otherwise, this kind of shape or reflector or some kind of waveguide or we have mentioned there or structures, we cannot go for this this one. Here one more uniqueness I will tell. This inside the liner, that metal liner is there. But once you are pressurizing that, because very thin liner is there, I think 0.4, 0.51 thin is there. Once you pressurize it, it will go in plastic stage. So the plastic stage with the help of composite, we can use in elastic manner. This is the unique process is there that we know this is auto filtration, where it can go plastic stage, and once it come back, the composite will play the role to make it elastic in nature. That also very unique property is there in these tanks. But what I was willing here to say that if you reduce that liner also, so very significant mass you can reduce, because the property of the matrix is not sufficient to take that kind of pressure. But I am going through with the literature that so many experiments is being done by our some NASA also I have read. They are going for the direct composite for this kind of high pressure application in filament product also. And this is pultrusion. This is regular process you are using. Okay, the lines of studies already we mentioned. Tooling in composite, tooling is very important to select, because we have to go for the curing, and we have to go for the product with lesser dimensional or lesser inaccuracy in the product. So we have to, because I have given this and time is not there to explain. So we can choose based on your application, based on your materials. And the machining of the composite, this is tricky because we are not going for any kind of this one couplant or this one kind of, so that the machining and their parameter to be chosen, so that the damage should not be translated in the final product. The defects, these are various defects is there, and there what the effect of this defect is there, that also you mentioned. So that we have to go for the very serious things. So if some kind of defect is there, so that health monitoring of the product is very essential, so that we cannot have the problem at the end of the time. So this engineering method is there. So what type of entity, and we can choose based on the available tools. Testing is very important aspect, characterization for the material and for the product also. So with the starting itself from the material per se, we have to go for the full characterization and that value and that kind of material property also only to be taken for the our design analysis purposes. These are the procedures and these are the test requirements are there. These are preparation of samples we have told. Quality control is very high essential in the composites because without this monitoring and because of this regard purpose, this quality control, if they are not there, then definitely some kind of misinformation for the product and that can lead for the further problem in the product qualification and testing. Scope of the research in the field of composite, what we are looking here, study on more on emphasize on the development of flexible high strain tolerant drilling system that is required to go for large antenna or large shape component for the space and this one 3D on fabric we are essential that we can have the kind of fabric that have the 3 directional properties so that we can utilize in a single layered on develop on CNT is also there. Improve on thermal conductivity and electrical conductivity is essential because you have explained there. And 3D printing on composite material because already we are there in a dirty manufacturing zone so that composite also can be 3D printed so that we can get disadvantage. Thank you all. Any question is there? You can.
Any questions?
Yeah. Yeah. Slide number? Oh. Ah. Which one? Carbon fiber.
Epoxy or Q&A ester, epoxy left bottom, carbon fiber oblique.
This one, the primary test, that is some correction is there that we have taken the image from the net. This is epoxy base or cyanide ester base. Why cyanide ester is required? Because epoxy is having some kind of that moisture absorption is more in epoxy. But cyanide ester is less moisture absorption. So that when we are going to space, so CME have mentioned, CME property can be utilized for this specific resin system. So that where the dimensional stable structure are required, where they like camera structure other things, there this kind of material is essential. And ester matrices. This is not cyanide is there, but some spelling correction is there.
Yeah, please.
Yeah. You mentioned you are using the honeycomb structure.
Yes, yes.
So how you make sure the honeycomb structure's holes are not poured with the resin, so the resin goes
Resin is not poured in the
at the
cell
holes
of the hole.
of the cell of the.
That's why if you see, because we have not go for any till in that process. If you see the honeycomb structure, we are putting that honeycomb core is there. Over that, two methods is there. That is a co-curing and that is a single curing. In that, we have to go for the pre-cured seeds are there. It can be for metal also. So that we are applying that one over the adhesive. You have to put the adhesive also and then you can put the seed and cure it. So the adhesive is very thin in the maybe 80 to 100 micron only. So that you see the cell of that core, there they will form the meniscus. That will generate the bond. So they will not go in the hole, they will just form the meniscus itself and they can bond with your seed. And one more process today our colleague was explaining, that is our reticulation. You can see the very high or very large kind of shape of there you can reduce that cell adhesive also. That is process reticulation. So that mask, because that is dead mass only, it is not going to help in bonding. It will just lie on your skin. But we want the bond to be generated within the cell of the honeycomb and your seed. That is sufficient to take. It is
So
not
what type of material you are using for?
You can use for the metal also, you can use CFRP, KFRP or anything, quartz, anything. That can be compatible with your adhesive. You cannot go for the differential, this one prepeg or this kind of reinforcement and different kind of adhesive. They should be compatible together and their curing cycle should be compatible with each other so they can generate the bond with your core. Core itself can be based on metal or non-metallic. So we are using Nomex core, QR core people are using. We have developed here a carbon core also. Here inside.
Did you try any lightweight, non-woven fabric for that?
Only thing you have to choose based on your application. It is not everywhere we can go for the honeycomb only. I have mentioned there is only you are using monocoque only. With the head is different structure where the compressive loads are required. Like payload adapters are there, EV shrouds are there, equipment base is there. But we have to choose this application. But these can offer in differential domain, differential property. But we have to combine them or we can choose differentially so that we can get the maximum property out of material. It is tailor-made property. No? Only CT cannot help us in a single fabric only. We have to, or fiber. We have to tailor it accordingly. We have to put the layer sequences. I will not gone in detail for design. Tailoring the material in the design direction orientation so that we can extract the third property or the resultant property close to the requirement. So the composite what best offers us is tailoring. Based on our need, you see the pressure water, we can have differential material. We cannot go for the hoop and meridian similar. So that is tailoring. That you can use. Anything else?
Which method are you using for this component for space application especially? Because there are so many methods for that.
Yeah.
But,
So I will just name it where I am working here in Science from the. We are using sandwich configuration for autoclave as well as this one out of autoclave, like vacuum bag and curing. There are filament binding is widely used in our other centers for the motor cases, for the piston tank and other ablatives and other things. So based on the application, we are choosing the process.
I think there are a lot many questions from Mr. Prashant Kumar. So people may enjoy his company during the tea time now. May I thank you, Mr. Prashant Kumar, for such a complete course on composite material. And may I request Dr. Ankush Sharma from Adira to felicitate Mr. Prashant. Please, sir. And in the meantime, let me ensure you, sir, that future is not that far. So the very next presentation by Professor Varun Sharma. Please join your hand. Prashantji, I assure you that future is not that far. Thanks for the nice presentation. And as he mentioned in point number 6, that additive manufacturing can be a game changer. So our next presentation by Professor Varun Sharma from IIT Roorkee is all about additive manufacturing of composites. So we are actually using at the academia level, and very soon we hope that we'll be in a position as a nation to deliver products to the space industry using printing and additive manufacturing. Professor.
A very good morning to all present. Thank you for having me up over here for this particular talk.
A video है ना sir?
Thank you. Very good morning to all present. Thank you for having me up over here. The presentation that I am going to make up, giving you a glimpse of what basically additive manufacturing is and how polymer-based composites could be manufactured using this particular technique. So giving you an overview of the giving you an overview of what basically additive manufacturing is. So we classify manufacturing primarily into two different domains. One is in which there is certain kind of a material waste, which we call as a subtractive manufacturing, which includes your machining, drilling, grinding, so and so forth. And the other way of manufacturing is in which there is a material addition, that is what is called as an additive manufacturing. So the lab that we have at IIT Roorkee is additive and subtractive manufacturing. So we work primarily in the both particular domains, but for the polymer-based composites, we are into additive manufacturing. So additive manufacturing has been defined as a process in which you fabricate up a product from a digital model. So we have two different kinds of a model. One is a digital, which is there onto a computer screen, and other one is a physical, which is coming out through that particular manufacturing process. So additive manufacturing is nothing but it is basically two-dimensional printing, which is being extended into the third dimension. So if I have a square and I start printing those particular squares one over the other, I land up into a cube. I start printing rectangles one over the other, I land up into a cuboid. Similarly, if I start printing circles one over the other, I land up into a cylinder. So this particular manufacturing has been primarily dealt up with the notion that there should be something called as a waste-less manufacturing. So there should be a zero waste. So that is what is the main point of fabrication of the processes using additive manufacturing. So this additive manufacturing is primarily categorized based upon the material that we are going to have. It may be in the form of liquids, it may be in the form of solids, or it may be in the form of powders. So when we are talking about polymer-based additive manufacturing, we are somewhere into the I will use this. We are somewhere over here. We are either into the liquid based, the molten based, or a polymerizable based. We are either working with the VAT polymerization, which is a commercially available name is a stereolithography apparatus, and the other one is a molten based, in which we are working with fused deposition modeling, FDM, FFF, which is based upon the material extrusion processes. So these are the most predominantly used polymer based additive manufacturing, but they have two different drawbacks. The first drawback is that whether you talk about FDM or SLA, which are there onto the screen, they have a limitation about the material that is available with us. So most of the material that is available, they are trademarks of certain companies. You have PLA, you have ABS, but there is nothing in between. So we cannot have a property which can cater up my particular need. So that is where there is a need of polymer composites to be developed, and to get those particular things done, there are numerous applications of this particular techniques, from product development, aerospace engineering. So we right now have a 3D printed post office in Bengaluru. We have 3D printed houses in Chennai. So there are numerous applications, from dentistry, architecture. The primary application which I will take up for the discussion is in the field of the biomedical applications. So in the case of a biomedical applications, we have the applications in terms of implant manufacturing, preclinical studies, surgical instruments, and one particular application is in the field of tissue engineering. So I give you a one particular case up over here. So if you see this particular diagram, I hope my cursor is there. So a person met up with a head injury and some portion of his skull got dissolved. It was not there, missing. So the periphery of his skull was not hemispherical, there was a cavity. So the doctors 3D printed this particular skull using certain additive manufacturing route and then get it implanted. Now, when this structure is to be used for certain load-bearing applications, and we start using metals in that particular application, there is a problem in a human body that is called as a stress shielding. The bones that are below that particular structure, they do lose up their particular strength, and they are no longer strong, or they are no longer stiff. So we can never always use metal for the biomedical applications. We have to rather use polymer, and because the polymers which are readily available are not meeting up the mechanical properties which are close to the bone, so there is where the composite of the polymers comes up into picture. So these are some of the applications. So earlier this tissue engineering which was being used, they have the problems in terms of high pain. There was a slow recovery. When the metal was being used, it results in a low bone density. So to get rid of this particular thing, so if there is certain kind of a cavity in that particular bone, so what we can do is we can design up a polymer based, composite based scaffolds, get that particular scaffold inserted into the human body. Now because these particular scaffolds have a interconnected structure, they have there is a porosity inside, it helps the human bone to regenerate on its own. So what happens is with time, particular scaffolds degrade into the human body, and instead of that there is new tissues that are being generated. So with time there is no point of there is a titanium implant into your body which needs to be cleaned frequently, so you can use up this particular technique for the applications. The traditional manufacturing route of the fabrication of the scaffolds include freeze drying, gas forming, phase separation, electrospinning, solvent casting. But the problem in all the traditional casting methods till date, when I'm saying till date, it means there is no solution for it, is that if I want to create up a hole of 10 microns, I cannot create throughout a hole of 10 microns with any of the process that is available. So the only solution for it is the field of additive manufacturing. So if I want to create up a hole of 10 microns, 5 microns or 20 microns with the same setup, just by changing up the drawings, that is the digital model onto the computer screen, I can fabricate any particular kind of stuff. So this is how the technique has evolved over time. So we were having up the first generation biomaterials, which were basically metals and alloys. Then we were having up the second generation biomaterials, which were primarily the bioceramics and polymers. Then we are having up the third generation polymers, which are nanocomposites, which includes PLA, PVA and all, and that is being attached with certain kind of bioinert or a bioresorbable polymers. And the fourth generation is where the tissue engineering of the scaffolds lie up. So the polymer nanocomposites, we use up a polymer that is of PLA and we try to reinforce it with certain biodegradable ceramics in terms of calcium phosphate, bioglass, HAF, graphene and graphite, so and so forth. So this is how we develop up the composite and use it for the 3D printer. So we use up a single screw extruder, we mix up the PLA with a constituent of a bioceramic, go it through a single screw extruder, develop up our own wires and try to characterize those particular wires whether their mechanical properties is good or not. So the most important thing that if we are developing up certain kind of new polymer composites, I need not to change the setup for that. There would be a standard setup, there would be a standard 3D printer. So if I am developing new, the material should be sufficient enough that it is being printed using the same 3D printer. So for that we try to characterize that particular material and try to find out that whether you are doing up the reinforcement of PLA with alumina, yttria stabilized zirconia, or you try to have up a hybridization of PLA with yttria stabilized zirconia, the glass transition temperature remains more or less the same. It means there is no change in the hardware requirement of a 3D printer. With the same 3D printer, you can even print a pure PLA and you can develop or you can print up the materials that we can develop using the process. The properties that we have, however, got, we should be able to show up our failures also. So the properties that we have got, we have found up that the tensile strength of the pure PLA is higher, but when you are reinforcing it with more and more of composites, the strength is at par. It is neither increasing, it is more or less remaining the same. Now there is a technical reason for that. The reason is that people have claimed that they can have a reinforcement of 30%, 40%, but practically it is impossible. Reason for that is the moment you have a high amount of reinforcement into the polymer to develop up a polymer composite, there is a lot of chances of the clogging of the 3D printers. there is a nozzle through which the material is being extruded up. So there is a large amount of chances that the material will not be 3D printed. So this is one particular domain which is there into the additive manufacturing arena, in which we want to develop up a 3D printing structures of polymer composites in which we can have up the mechanical properties better than that of the parent material. So in this particular leg, we found up that whenever we are developing these particular polymers, if they are being to be implanted into the human body, then the material should be hydrophilic in nature. There should be a spreading of the human body fluids onto that particular scaffolds. So what we found up is that as compared to PLA, the mechanical properties is comparable. At the same time, these composites that are being developed, they are also hydrophilic in nature. The water spreadability is good. It means it is a region about which it can be used for the biomedical application. At the same time, it's not only about the material property that we are going to play up with, it is also the structure that we can play up with. So people are right now also using titanium for the scaffold industry, but titanium has a very good mechanical properties as compared to that of the human bone. So how can we make it close to that of the bone, which is very spongy in nature? Outer shell is hard, inner is a sponge in a human bone. So how we can make up the material properties close to that of the human bone? The second aspect is by changing up the architecture of that particular material. So we can create up certain kind of a porous structures within that particular material. You can use titanium, you can use polymer, you can use any sort of a material. You can create up these different kinds of structures and try to have up a mechanical properties which is close to that of a human cortical bone. So these are some of the structures that we have printed, and the surface roughness that we have achieved is somewhere close to that of 1 microns, that it can be used for the biomedical industry. This is the example in which we try to analyze that if we are using it in the human bone, there will be always a constant friction between two different joints and all. So whether this particular structure or whether this kind of a polymer composites could be used for that particular thing, we found up that based upon these structures, the coefficient of friction between the mating parts in the human bones is close to that of 0.15, which is within the permissible limits. These are some of the other characterization that we have done. So we have tried to have up the mechanical properties of the polymer composites which are close to that of the human bone. We have tried to check up the testing of that particular polymer composites. The other thing is that when these kind of structures are being put inside into the human bone, whether they will be toxic or at what will be the time of degradation of these particular polymer composites. So for that, this is the wettability studies that we did. So if you see that for a pure PLA, the contact angle is 81 degree, but the moment you are adding composites into it, the bioceramics into it, the wettability angle is reduced to 41 degree. It means there is a better spreadability of the human body fluid onto that particular scaffolds. So better would be the spreadability. It means better would be a tissue generation, better would be the tissue that would be growing within that particular pore architecture. So we have been able to have a pore size close to that of 1 mm. That is what we have achieved through our particular set of research. So at the same time, when they are being put up into a human body, they are able to degrade within 28 days from 100% to 94%. We do not want that when the polymer is being put up or the composite is being put up into the human body, it degrades within a fraction of days or so. Because the human bone will also take sufficient amount of time for itself to grow. So if you see it, within 28 days, the degradation is just from 100 to 96%. So it means that there is a sufficient time for the human bone to regenerate from that particular bones itself. So these are some of the compression tests and the roughnesses that we have been able to achieve. Now this is where we fabricated a scaffold and then tried to see that whether the human bones grow or not. So for that we tried to have a PITS testing with the rat cells. So if you can see up from this particular diagram, so whether you are working for the PLA or the PLA with certain kind of composites added into it, then even then there are live cells onto it. So we introduce certain rat cells onto that particular scaffolds, and there is no kind of toxicity that these particular scaffolds are being generating. So these are some of the biological studies to categorize it. It's not only in the field of the bioceramics and all. We have tried to have up its addition with the naturally occurring composites also, like the calcium phosphate we used over here as a ceramic. So these are some of the testing for that particular stuff. Now, the most important thing when we are talking about that we have to fabricate these structures and use it for the additive manufacturing domain, then one particular thumb rule, so if we are developing it for the world, so one particular thumb rule that we need to have is that whatever the filaments we are going to manufacture, that should have a uniform consistency. So if we are manufacturing it and then shipping it to somewhere, the ideal dimension for any particular 3D printer in all the worldwide is 1.75 mm. So with the additions of 5 to 10% of these ceramics into the polymer, we are able to have up the dimension of that particular filament close to 1.75, means there is no need of changing of any particular hardware of the material. These are some of the structures that we have been able to print, nautilus cell, honeycomb, so and so forth. The vision of this particular research is we want to have up a minimum invasive surgery. Now, if there is a stunt into a human body, right now the people are they create up a very small hole into the human body and then they put up a stunt in. Then there is a ballooning effect, and then that particular, when it reaches to that particular vein, it balloons up and removes up the clot from that particular position. So we try to have up the fourth dimension of the printing, which we are calling as the 4D printing. So what we are having in this particular stuff, I will quickly take up you to the video. This is the permanent shape. The permanent shape is being compressed. They are given a certain kind of a temporary shape, and when it is being subjected to certain kind of a stimulus, it comes back to its original position. So the polymer composites have been taken up into that particular extent. So if you look to this particular video, this is a PLA which has an origami structure. It is being crushed up, given a temporary shape, and then this PLA ceramic regains back to its original position when there would be a stimulus. So this is the permanent structure printed using FDA. It is being compressed, deformed, and then it is being subjected to a water stimulus, and when it is being subjected to 70 degrees centigrade, it bounces back to its original position. So we have found up that it is being applicable for the scaffold industry also. So this is the compression, if you can see up over here. After the stimulus, it is bouncing back to its original position. There is a shape recovery. So from this particular thing, we found up that we can have up a shape recovery close to that of 98%. So even if you are compressing it, you have compressed it down, the bouncing back of these polymer composites is close to 98%. So that is one more area of the polymer composites which can be dealt up in the space sector, and that can be also dealt up with the medical sector. So I hope I am there on time. So that's all from my side. Thank you.
Yeah, please.
Yes.
There
is no
resin cracking or resin craning is not happening, but
no, there is no cracking. So if you see to this particular thing,
I have seen that the temperature is less than TG somewhere you mentioned.
that's the glass transition temperature. Above 70 degrees centigrade, it is bouncing back.
You have mentioned when you have to crush it. There also you have to taken care of that temperature range.
No, it's at room temperature. Crushing is at room temperature.
But there is no resin cracking.
No cracking. This is PLA plus ceramics.
Any more questions? Okay. Thank you, Professor Varun, for such a nice, knowledgeful session. And now, may I request Professor Suja Ahmed to facilitate Professor Varun? Sir, please. Kindly join your hands together to welcome Dr. T.V. Sri Kumar, now enlighten us with their works on acrylic precursors for carbon fiber. Sir, please.
Very good morning, all of you. Thank you very much, Mukesh ji, Chairman Indoor Composite, and also Dr. R.K. Singh, giving me this chance to deliver my work or the work which we are doing at the Bombay Textile Research Association. High tenacity acrylic precursors and carbon fiber and India strategy. You can see that yellow fiber, which is the precursor for carbon fiber. I hope all of you know about carbon fiber, and which is one of the most important material that is needed for composite industry, and which is something which we don't have in India. So we have to always depend on the imports. So we need to at some point become independent of these restrictions that we have. The yellow fiber which you see, that is the precursor for carbon fiber, and the black one is the carbon fiber which is made out of it. Because you know that polyester can be made by melting polyester and extrude it and do a melt spinning, and you can make a polyester fiber. Polypropylene is also same way, polyethylene also same way. But how will you make carbon fiber? You cannot dissolve carbon and convert it into a carbon fiber, or you cannot melt carbon and convert it into a carbon fiber. So the process is, you first take a precursor, the yellow fiber which you have, and then heat it to various temperatures up to 1000 degrees Celsius to convert them into carbon. Because all the polymeric material, they have carbon, hydrogen, nitrogen, and a little bit of oxygen. So you have all the carbon-carbon chain, and oxygen is, or hydrogen is at the other side. Like if you take polyethylene, it is CH2, 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 CH2. So if you remove all the hydrogen by heating, so you will get carbon remaining. But the problem with polyethylene is that if you heat it, it will start melting. So it will no more be in the form of a fiber. So what you take is, one of the most important precursor for carbon fiber is acrylic fiber. Acrylic fiber is common, which is used in making sweater also. But for making carbon fiber, you need special acrylic fiber. And that special acrylic fiber is called a high strength precursor. So if the strength of the precursor is very high, the strength of carbon fiber is also going to be very good. If you compare the strength of normal acrylic fiber, which is used for sweaters, is about 3 to 4 GPD, grams per denier, in the textile terms if we talk about. But that of the precursor, carbon fiber precursor, is above 6 grams per denier, 6 to 7 grams per denier. So here, I'll be describing shortly about how we make precursor and how we can convert that into carbon fiber. And the work which we have done at the Bombay Textile Research Association with the help of the National Technical Textile Mission. And now we have that Technical Textile Mission in India. It's about 1,400 crore they are distributing. I think most of the academic institutes might have got part of it, depending on their project proposal. So we also received about 21 crore for developing carbon fiber precursor in India. As you have seen, see, these are the high performance fibers which are very important in the composite industry. Ultra high molecular weight polyethylene, which goes into bulletproof applications, we are importing it. Kevlar, that is again required for bulletproof, for making hard, bulletproof material like helmets, and that is also being imported. And carbon fiber, which is required for all the aerospace applications. The previous presenter also has mentioned that the lightweight is very important to have a high payload. The lightweight and strength. So the strength to weight ratio is very, very important to have high payload in aerospace industry. So that is also being imported. Only glass fiber to some extent is being manufactured in India. So we need to create all these high performance fibers. So there is an opportunity in India to have all these fibers, which is very much required if we have to become a Viksit Bharat. So the properties, if you compare the properties of normal fibers with carbon fiber, what do you see? The acrylic fiber, which is the textile grade acrylic fiber, is about 0.4 gigapascal, and that is the precursor is much higher. And if you consider the T300, that is the basic carbon fiber which goes into aerospace, which has proven the airworthiness, is T300. The strength is about 3.5 gigapascal, and steel is 1.3 gigapascal. And the specific strength, if you consider, that is most important, the strength to a density, the strength divided by the density. The highest is 3.5, again for the carbon fiber, and that of steel is only 0.17. So the development of carbon fiber is very important if we have to go for a high strength, low weight structure. Carbon fiber, the area of carbon fiber where it has been made is for clean energy, energy saving, conventional energy, and high performance materials, starting from windmill to gas turbine. These days, drone is one of the things which is growing very, very, very fast. Almost 5,000 manufacturers already we have in India, and all this has to be in carbon fiber composites to have lightweighting and longer range. So very, very important. And India is also making in defense the Rustam UAVs, unmanned aerial vehicles. That also is, mostly used with carbon fiber with different composite manufacturing technology. In conventional energies, for deep water excavation, oil excavation, it's very important because carbon fiber is something which will not have any corrosion effect, and it is used in atomic energy also and high performance materials. The word carbon fiber has grown very sharp because the industrial carbon fiber applications were used in energy, clean energy applications. So aerospace also has grown quite well, and in 2020 it was about 120,000 tons per annum of carbon fiber manufacturing has happened over the world. The economics, we can debate on this. This is something which I have considered manufacturing aerospace grade carbon fiber, because industrial grade carbon fiber is coming out much cheaper, like $20-25. If you consider like $35 per kg, then the payback is like 4 years. So you can manufacture it. So in normal case, if you have a polyester plant, the payback is 5 years plus. But if you have carbon fiber, the right kind of technology, so with 4 years is quite good kind of payback which one can expect. So the industry has to come forward and start manufacturing carbon fiber in India. So the process of making carbon fiber is that we need to have first a polymer, that is the acrylic polymer suitable for making carbon fiber. It is different from that of conventional acrylic fibers. So there is a special polymer required for carbon fiber, and we have created this technology in the Bombay Textile Research Association. And that polymer has to be filtered, then dried, pulverized, and then again you have to redissolve it in a dope tank, where you can make a honey-like structure, honey-like polymer. It's a very transparent polymer solution that is called dope. The dope is further spun through spinnerets and then converted into a precursor fiber, the precursor binder which I have shown, that the yellow fiber, and then it has to be heated at 230 to 300 degrees Celsius. then carbonized at 1200 to 1800 degrees Celsius to make carbon fiber. So it's a long process. It is not as simple as like if you make polyester, where you have polymerization, then melt spinning, winding, you got the polyester fiber. But here, polymerization itself is one process. Then dough preparation, spinning, converting into the precursor fiber, then stabilization, then carbonization. So it's a process is quite long process, but ultimately you will be getting a very nice material. So another thing which we have done is not just conventional carbon fiber. We try to incorporate carbon nanotube in it. And I hope all of you know about carbon nanotube, which is one of the strongest material where the theoretical strength of carbon nanotube is, single wall carbon nanotube is 50 gigapascal. And that of a normal carbon fiber is only 3.5 gigapascal. So what we are thinking is that if you can incorporate this carbon nanotube in the precursor level itself, that will reinforce the precursor directly. So you will have a CNT reinforced precursor, and once you carbonize it, this will give additional strength to the overall carbon fiber. Or during the carbonization process, carbon nanotube itself is a perfect carbon fiber or a nano level carbon fiber. So they will lose its own identity and the whole thing will become carbon fiber. And additionally, what we found is that during the heating process, if you see here, the change in length percentage, A is that of the pure precursor, normal precursor, while heating, B and C are precursor containing carbon nanotube. That shrinkage is much less. If you see the dimensional change here, A shrinks much faster during the heating process, but B and C doesn't shrink that much. What does it mean to the production? If it doesn't shrink during the thermo-oxidative stabilization process, you can have a higher speed, line speed, during the all precursor production process. So during the precursor production, if it shrinks, then you have to reduce the winder speed. So here you can have a higher speed during the whole precursor and also the stabilization and carbonization process. You can have a higher line speed, then you can have a higher production capacity. So you can reduce the cost of carbon fiber. So if you have a little bit of carbon nanotube in it, so the production cost will reduce further. So if you can make a carbon fiber at $15 per kg or less than $15 per kg, you can easily compete with glass fiber. So all the glass fiber you can substitute with carbon fiber if one can make carbon fiber at the cost of $12 per kg. So this is a very important thing. So what you see here, the first one, the oriented pan reinforced CNT. So the precursor containing carbon nanotube in between, that will restrict the whole polymer to shrink, and also it will stop the breakage process, where here you can see that the only pure polymer will break in between. So what we have shown here is that at Bombay Textile Research Association, we have the whole system of making the precursor, where we have that first reactor where we can make the polymer, about 40 kg, and that one polymer solution, we can convert it into in this second reactor, and then do the whole spinning. I'll show, I hope this video work. Yes. So this one, the polymer is then pushed in through the coagulation bath. So you can see, I hope you can see the fibers that's coming out, the 1000 filaments. Yeah, you can maybe show it to others. The precursor we have made. So it's about 1000 filaments here. Sorry. So you can see this fibers that's coming out. after the coagulation process. So there are about 1,000 filaments. So we have the capacity to make 1,000 filaments, 2,000 filaments, 3,000 filaments, and 4,000 filaments. So 3,000 filament is a standard industrial level of production in minimum 3K is for aerospace applications is much better. If the 3K is most expensive, then 6K, then 12K, and above 12K, 24K, and it's industrial carbon fiber. So we can make 1,000 to 3,000 and 4,000 also. So this is the coagulation bath. Now this is going to the washing baths, second coagulation and washing. And this is another washing plus stretching. It says it's a special technology. It's called the draw duo, and further drying and spin finish addition. And this is further stretching and collapsing of the pore porosity, and also heat setting. And then it goes to the winder. So this industrial winder is in worldwide, everyone uses the same winder, sham winder, which is being used for the precursor winding. So this is how we made the precursor fiber. And we have also done some preliminary study on the carbonization process, and it is giving good kind of carbon fiber also. So we have the capacity to make 1K, 2K, 3K and 4K filaments at the Bombay Textile Research Association. This is one of the, I think, India's first this kind of a machine that which we have and the process that we have developed. Thank you. Thank you. And if you consider the properties of the precursor fiber, 6 grams per denier is the minimum requirement. So what we have is about 7.39 grams per denier. This is one of the good strength, and also 1.1 to 1.17 is the denier requirement. And these are the properties that international available precursors they have. It's about if you can see, it's about 0.12 linear density is 0.1 text, so that is equivalent to about 1.2 grams, and the tensile strength, if you see the filament numbers 3K, 6K, 12K, so we can now produce all these kind of filament diameter, denier, and also grams per denier fibers. The most important part, which I was talking about, the shrinkage part, the shrinkage reduction, which carbon nanotube is established here, and this is a work which we have done in the laboratory in a batch process by heating the both precursor fiber and the just precursor and also CNT reinforced precursor. See that the black one is the pure pan, which shrinks much faster, and the red one that is pan CNT, the right one precursor, and it doesn't shrink that easily. So this restricts, the carbon nanotubes actually restricts the shrinkage, and that is one of the most important property that we have. And the panox which we produced, the oxidized pan which we produced, have about 2.2 grams per denier. 2.2 grams per denier. You can see here 2.2 grams per denier, and that of pure pan is about 1.6 grams per denier. And this is equivalent to the internationally available panox. The panox normal strength which is available internationally, you can buy, that is about 2 GPD, grams per denier, and what we have 2.2 grams per linear after introducing some amount of carbon nanotube. So this we need to further improve the whole this process, but we can make same amount, the same kind of property in India now. So we have this technology available. So I urge all the people to collaborate with our institute so that we can make it commercial scale. With that, thank you so much. If you have any questions.
Any questions from audience?
Yes. Okay.
The basalt fiber also produce this technology.
Basalt is a melt process. Basalt is a melt process. Yeah, that is, I think, basalt is a stone-based, it's a mineral-based fiber. So that is a different process. Yes.
Can we use this precursor in type 4, type 5 cylinders manufacturing?
Yeah, once precursor is, you have to convert that into carbon fiber. Once you convert that into carbon fiber, yes, you can use in any of the, because the strength we expect, like from 6 grams per linear fiber, one can easily make T300 and even 400. So with 7.2 grams per linear, definitely we will be able to make much stronger carbon fiber. So T700 carbon fiber easily we can make. Yes, sir.
You mentioned the process of that block flow diagram as to how to reach from pan to...
Yes, yes.
At what stage of the process is the CNT infused?
The dough preparation. During the dough preparation, yes.
You told that carbon fiber is cost compared to the carbon fiber. So we started speaking about can reduce up to $10, $8. So it can be comparable or can be usable for more.
Yes, yes.
But while importing CNT, so how the cost will be because it will increase. CNT is the material. So we are negotiating.
Yeah. Yeah, that's a very good question. The CNT concentration here is very, very, very less, 0.05%. So very low concentration. If you use a higher concentration, then the dispersion of the nanotube is very difficult, because then it will act as a defect size rather than reinforcing. Because at higher concentration it will not go inside it itself. So what we do is we make very small quantity, 0.05% in DMF or DMFC solution, and then that we mix with Pando. So that small quantity is enough. So that cost is less, much less. That you can get that advantage in the line speed directly. Because when you add carbon nanotube, all fiber becomes stronger, so you can have a higher line speed. Both in precursor spinning and also while making the panox also. So the overall speed of production is much high, so that advantage nullifies the cost of very small amount of carbon nanotube. Yes, sir.
So this 0.05% is based on like optimization of the cost, or is it a sort of kinetic study which has been done to arrive at that 0.05%?
Okay, what we have done is we have done even 0.012%. So what we found is a 0.05 is the much easy and getting the without compromising the strength of the precursor fiber.
That it will be working.
Yes.
Is there any effect of molecular weight of the precursor pan on the effect of the strength of the carbon fiber after carbonization?
Yeah, absolutely, yes. So
is there any effect of means what is the typical molecular weight of the precursor pan for this particular material?
Yes. So we normally measure the intrinsic viscosity. So the intrinsic viscosity about 1.6 to 1.8 grams per dl per gram, deciliter per gram is the most ideal. For that 1.6 to 1.8 deciliter per gram is equivalent to about 1.3 to 1.6 lakhs.
Which solvent we are using for that particular viscosity measurement?
Pardon, sir?
In which solvent we are
DMF. So all these studies, all the solution viscosity studies are done in DMF.
Thank you, Dr. T.V. Sri Kumar, sir. May I Professor Sunil Kale, Dean, School of Engineering and Applied Science, to please felicitate Dr. Sri Kumar for the nice presentation, and I must, on behalf of all the citizens of India, congratulate Vitra for the development of nano-carbon reinforced fiber cell. So it's a great.
I invite all of you to
a-
visit our institute.
It's a great step towards the, at some point we are ahead of the world.
Thank you,
So
sir.
I congratulate the entire team. Thank you. Now may I request everyone to please join outside in the exhibition hall for the cup of tea, and respecting everyone's time, shall we meet in 10 minutes time here so that we can begin in time. Thank you. See you soon.
टाइम ले लिए ना.
ना कोई बात नहीं, अच्छा था सर, आपका बहुत अच्छा था. इसको कुछ देखिए और लिखिए यहाँ से, ठीक है. अब इसको
डिलीट कर दिए ना.
ये भी यहाँ से भी डिलीट, गॉन. चेक कीजिए.
अरे हमको चेक नहीं करना. 10 तारीख में क्या है?
सर
यही से.
हमने 9 में डाला था.
अच्छा प्रोफेसर बाबू. अच्छा 10 में नहीं डाला था.
9 में डाला था. 9 में ये
आप यहीं के एम्प्लॉय हो गया?
हाँ, यहाँ पर
कहाँ पे?
अहमदाबाद इंस्टीट्यूट टीम में.
विजय का नहीं है इसमें? विजय
नहीं सर,
किसका है?
ये तो कल वाले से, कल का है, कल वाला कल बन.
विजय का देखो कहीं पे.
ये तो सर वो तो फोटोग्राफ है, फोटोग्राफ से.
विजय का नहीं है क्या इसमें? विजय वाला कहाँ रखा है?
वो डिलीट कर दीजिएगा.
हाँ, वो मैं डिलीट कर रहा हूँ सर.
ठीक है ना.
ये रहा सर का, आपका सर, ये भी मैं डिलीट कर रहा हूँ. शिफ्ट डिलीट सीधा बाहर.
सिंगल से भी कर लीजिए.
यहाँ से भी प्राइवेट नहीं.
ठीक है.
और वरुण शर्मा सर क्या है आपका? ठीक है सर, उनका बाकी थोड़ा बाकी चलो तो ये वीडियो
यहाँ ठीक स्लो मोशन में रिवर्स कर दो. 0.5 में कर दो.
पॉइंट का मारने से माउस तीन रखो इसमें.
कर दो तो 1%.
बड़े हम कल बड़े इतना कर चेक करें दी.
शो
शीट माइक
Hello, sir.
Yeah, hello, sir. Good morning.
Welcome back. So I hope you all of you had a nice tea session, and Professor Dr. Bala at his own place, since he is not physically in person present here. So welcome back once again. So I now request Dr. Balakrishna Prabhu S from College of Engineering Guindi, Anna University Chennai, and since morning and since yesterday rather, primarily we are focusing on fiber reinforced composite. We'll have another aspect of the composite industry, that is challenges in metal matrix composites processing and mass production. So over to you, Dr. Bala.
Yeah, thank you very much, the organizing team, and especially Dr. R.K. Singh, sir, for giving me
Sir,
the
may I request you
opportunity.
to please place the mic suitably? Your voice is quite less.
Okay, okay, 1 minute, 1 minute.
Just 1 minute, sir. Sir, can you just unshare the screen? Sir, you can start now, sir. Sir, am I audible? Sir, your voice is not coming, sir. I think you are on mute. No, sir, you are not audible. Just a minute, sir. We can't hear you. Just-
Hello.
So probably your microphone is not connected. Can you please unplug once? If you can hear me. Hello? Hello? No, sir, we can't hear you yet. Could you please unplug? Can you hear me? Just raise your finger or thumb so that we get to know. Okay, fine. So,
I can hear. Can you hear my voice?
yeah, loud and clear now, sir.
Now loud and clear. Okay, okay. I think I can go without a microphone. I think the microphone has created some problem. I think now you are audible. My voice is audible.
Yeah, please go ahead, sir.
Yeah. So thank you very much for inviting me to deliver this talk on the challenges in metal matrix composite processing and especially in mass production. And you might have come across the polymer matrix composites, and also you have witnessed several components and applications make use of this polymer matrix composites. And in our day-to-day life, we might have come across so many components that are, as a result, see, the polymer matrix composite processing is very well established, and as a result, it has penetrated into the industry market. Now, the metal matrix composites, even though no, you have very good mechanical properties and very good benefits, and this metal matrix composite still it has a lot of problem. As a result, it is not penetrated into a industrial market. So the problems that are hindering this the market penetration, probably in the research aspects, we will address. So as you know, the metal matrix composites in general consist of two or more chemically distinct macro constituents separated by a distinct interface. Sometimes in the metal matrix composite, we used to say interface because the interface is a common terminology. And in this composites, we the high temperature processing involved in it, we end up with the interface. A different pace will be generated at the interface. So as a result, it would be interface. So usually these kind of MMCs can be made from pure metal or alloy. Sometimes, most of the cases, we go for alloy metal, and especially with the non-ferrous metal. So aluminum alloy or magnesium alloy or copper alloy, we try to convert that into a composites. As a result, the weakness of the metallic material will be overcome by reinforcing the reinforcement. And also we have a higher ductility and toughness than the ceramic and CMC. And also here the role of the reinforcement in MMC is to increase the strength and modulus, as similar to the polymer matrix composites, where we improve the strength and also the toughness and modulus. Similarly, in the MMCs also, our main objective is to increase the strength of the metal and increase the strength modulus of the metal, so by reinforcing. So, and also the MMCs have temperature capability, generally higher than the polymer. So the thermal stability of these metal matrix composites are little higher than the metal. As a result, you have a very good high temperature capability. Then low to moderately reinforced MMC is formable via processes normally associated with the unreinforced metal, meaning what all the conventional methodology you have to process the metal, the similar methodology we can also adopt to manufacture or process metal matrix composites. As a result, the technologies are not new. It is only the modifications of the conventional technology that we employ to manufacture metal. So therefore, the technology wise, it is not a newer technology that we are going to talk about. It is all conventional technology, but we need to have some kind of a little modification to manufacture or process composites. These are all some basic things that the metal matrix composites can be classified into dispersion strengthened, particulate strengthened, and fiber reinforced. And especially the fiber reinforced would be similar to the polymer matrix composite, where we have a lot of opportunity with respect to the particle reinforced composites and dispersion strengthened composites. These are all distinguished only with respect to the particle dimension. If the particle dimension is more than 1 micron, we used to call that is a particle reinforced. And if the particle dimension is less than 1 micron, we call that is a dispersion strengthened MMC. So the principle is very simple. In the fiber reinforced composites, the fibers take up the strength. So that is a major load carrying member, and as a result, the strengthening mechanism is fiber strengthening mechanism. But in particle reinforced composite and dispersion strengthened composite, the particles that will be acting as a hindering element to dislocation movement. As a result, now you have good degree of improvement. So in general, now we have aluminum, magnesium, titanium, copper alloys, super alloys, and majority of this metal matrix composites were already tried with aluminum and magnesium. And we take this reinforcement, mostly the silicon carbide, graphite, or alumina, so in the form of a particle or fiber or in the form of a whisker. So coming to the processing technology, and if you want to have a mass production, and we are depending on two technology. One is solid state processing and liquid state processing. And in the vapor state processing, somehow now you can make a batch production. And for high-end application, we still fabricate some of the MMCs with the vapor state processing. And solid state processing technique also possible with mass production concept, but because of the size limitation and also some of the inherent problem associated with the composite technology when you take up the solid state. And so far it has not been fully used for commercializing the metal matrix composite, but the research field we are using the solid state processing to demonstrate some of the mechanical properties of metal matrix composites. So the liquid state processing from the industrial perspective, it would be the convenient method to have a mass production technology of metal matrix composites. So here now we have three different stages of pre-processing and primary processing and also secondary processing. And this liquid state processing technology especially useful for particle or short fiber or a chopped fiber, or probably for a continuous fiber also in case of a preform preparation. And the major technology associated with the liquid state processing are stir casting, then we have an infiltration, then we have a spray casting technology. And among this, the stir casting is the one of the important technology where there is a possibility of mass production. So it is a conventional technology, little modified. So in the primary processing stage, why it is called a stir casting? Because we add particles or chopped fiber or short fiber and try to stir it to homogenize this particle distribution or short fiber distribution. So stirring is necessary to have a homogeneous distribution. So once the stirring helps to have a homogeneous distribution of these reinforcements inside the metal, then the conventional casting methodology will help, where you cast it and then try to have a secondary machining operations or joining or whatever purpose for which you are making this composites. And in the infiltration process, the preform will be prepared either out of a continuous fiber or a short fiber. And by the infiltration, like a gravitational infiltration or pressure assisted infiltration, you try to infiltrate the liquid metal, and finally you end up with the composite. So the spray casting, where you are going to spray the liquid metal over the reinforcement and layer by layer, and then try to consolidate. Now what I am going to talk about, it's only the liquid state processing, because that is only the technology. Probably if you overcome the barrier of these technologies, then there is a possibility of mass production. So the industry can think about making some good composites in a mass production and then use it for a different application. So in the stir casting and the liquid state processing, where the stir casting, we can have a metal yield of 90%, and then range of volume fraction of reinforcement addition is 0.3. That means 30% of reinforcement in terms of a volume that can be reinforced. And also no damage would occur for this reinforcement, and it is least expensive. And associated technologies of this liquid state processing, we have a skew casting. Then in the skew casting, we can go up to 45% volume fraction. That means in the fraction it is 0.5, in terms of percentage 45. But sometimes no, you have some damages on the fiber or particle because the pressure is applied, and also it is moderately expensive. And the powder metallurgy compared to the liquid metallurgy, it is highly expensive. So for a commercial production and for a mass production, it would be possible no, to take a stir casting technology. The technology is very simple. No, you try to heat the metal and make it in a form of a liquid, and superheat the liquid and try to add the particles, whatever may be the reinforcement particle, silicon carbide or alumina or any other particle. You are going to add and try to stir it mechanically or probably ultrasonically. So some kind of a stirring to create turbulence is necessary, so that the particle will homogeneously mixed, and it will uniformly distribute. Once it is distributed, then by conventional way of deposition, that means casting certification, you can do it. So these are some of the microstructure in our laboratory that we have casted. So you could be able to see the particle distribution, which are in some cases it is agglomerated. The particles are agglomerated. Some places the aluminum is left without any particle presence. That means the microstructure is highly inhomogeneous. It is not homogeneous microstructure in some of the cases. In some of the cases, we could able to achieve the microstructure uniformity. That means the particles are well dispersed and there is no agglomerations possible here. And when you have so much of agglomerations, one thing that's noticed here, it's that, so you could see a lot of porosity associated with the agglomerated structure. And that's the one thing. So because melt will not be allowed to go inside the agglomerated structure, so melt will be stopped here. It's a barrier. So as a result, now you form some porosities also associated with the part clusters wherever now you have. But when you have a kind of the uniformity, there is a homogeneous distribution, and you can also minimize the porosity, and you can also expect it to have good mechanical properties associated with this processing condition. In general, even though this technology gives a possibility of mass production, but there are some challenges that are associated with this technology. Is that the one thing is difficulty of achieving a uniform distribution of reinforcement material. See, that is the one foremost challenge of this technology. So once you achieve a homogeneous distribution, that you can also work on improving the properties of this material. Another thing is that the wettability issue, because the metallic material and a ceramic material you try to bind, and as a result, the wetting would be the problem. Another case is the chemical reaction, because most of this liquid state metallurgy processes will take a minimum 30 minutes to an hour. As a result, there is a continuous conduct of this reinforcement into the melt at high temperature, slowly develop some reactions between the matrix material and reinforcement material. So you generate some chemical reaction product at the interface. Sometimes that gives you an undesirable byproduct that stops the bonding between the matrix and reinforcement. So as a result, we cannot get composites with good mechanical property and good reliability. So the porosity can be eliminated. That is not at all a problem in a mass production. So we have a technique to control the porosity. But the main challenges in the metal matrix composite production is the three, I would say: difficulty of achieving uniform distribution of the reinforcement. Then we have the porosity, the chemical reaction, then the wettability. See, the uniform distribution, supposing, for example, if it is controlled by the viscosity, and here we have a viscosity relationship here, which is the inverse proportion. So the relationship between the viscosity and temperature is given here. It has an inverse proportion. That means when the temperature is high, melt temperature is high, the viscosity will be lower. So when you have a melt which is kept exactly at the melting temperature, and addition of reinforcement in it, the reinforcement absorbs the temperature. As a result, the melt temperature will be drastically reduced. As a result, now viscosity will be very, very high. So it won't allow the particle to disperse inside the matrix material. So because it is highly viscous, it would never allow the particle to penetrate into the viscous medium, and as a result, more agglomerations would be formed. So if you conveniently set the temperature parameter a little high, you will have a lower viscosity, which will be sufficient, where the particles will be penetrated while the turbulence is created. It will go around and then uniformly distribute. So one controlling parameter in this process is the temperature. So the temperature may play a major role in controlling your particle distribution. Okay, so by controlling, probably here you have a data which we have calculated that the aluminum alloy, the viscosity is drastically reducing from the melt temperature to 900, but when I add 10% of silicon carbide particle, the viscosity is even very high. So that means it is high viscous medium. So distribution is very, very challenging. So probably at 900 degrees centigrade, I would get the viscosity similar to the pure metal. So that would be possible where now you can disperse this what is known as the particle. So here I present the three cases. One, the melting temperature 650 were preheated to 700 degrees centigrade, where particles are stirred and casted. Finally, at 700 degrees centigrade, we end up with a more amount of agglomerated kind of a structure. So silicon carbide particle, I could see agglomerated form. And when I try to increase the temperature to 800 degree, the agglomeration was broken, and you can able to see a good homogeneous distribution of this particle. And again, when it is increased to 900 degrees centigrade, further agglomeration starts. So that means, the temperature, only by increasing the temperature, one cannot achieve good homogeneity, because something is happening there. So you have to have a sufficient viscosity to allow the reinforcement to penetrate and then uniformly distribute. But even if you have too much of low viscosity, that try to allow the particle to settle down very quickly a moment you stop the process and before the casting. So that also try to make more particle agglomeration. So therefore, extreme lower temperature is also not favorable, and high temperature is also not favorable to have a homogeneous distribution of a particle. That results in mechanical properties also. See, when you have a 800, you have a homogeneous distribution. As a result, now you got to have a good mechanical strength compared to the parent 700 degree processed condition. Okay, but in the 700 as well as 900 degree conditions, the strength is also declining. That means one has to optimize what would be the temperature to get homogeneous distribution. So the temperature effect we have studied. Then also another important thing is the wettability between the main substances. So it's the ability of a liquid to spread on a solid surface. So that means, one can increase the wettability by increasing the surface energy of a solid, that means the reinforcement, and decreasing the surface tension of a liquid, that means the matrix metal. So the decreasing surface tension of the matrix metal in the liquid is possible by increasing this temperature. So the viscosity will come down. And again, increasing the surface energy of the solid is by means of heating the solid, preheating the solid. So these combination will make a decreasing solid liquid interfacial energy at the particle matrix interface. So the wettability can be decided with the angle, wetting angle. So you have a tension vector. So it is surface tension vector of solid liquid and surface tension vector of liquid vapor. So the angle between that. So if this angle is 0 or close to 0, we call perfect wetting. And preheating the ceramic particle to 1100 degrees centigrade gives the angle 45 degree compared to 900 where you have an angle 150. So therefore, preheating the particle before adding into the melt helps to improve the wettability. Okay, and also another way, so the agglomeration, it's not only happening because of the settlement of particle, because of the lower viscosity. It's also possible, redistribution is also possible, because during the solidification, the metal try to solidify. As a result, you generate some kinetic energy in the solidification front that pushes the particle in the front of the solidification. As a result, you have some agglomeration possible. So if you control that driving force by applying a compressive force over that, then homogeneous distribution, what happened in the melt would be produced in the solid after casting also. Therefore, the skews casting would be the another secondary operation. Once the stirring is over, then you can probably transfer the melt to the process where no you do a skews casting, where you can also get some good microstructure that helps to improve the mechanical property. So here, these are all the process parameter that we have studied, from varying the melt temperature from 700 and 750 to 900, and keeping the die temperature also in a different situation, 250 to 400 degrees centigrade, and also by changing the pressure from 30 MPa to 120 MPa, how microstructure is changing that we have seen. And this zero skew pressure is something like a conventional casting. So that clearly indicates that you have a lot of agglomeration. Even though you assume that in the melt, you have created good condition where agglomeration is not there and you have a good homogeneous distribution. But after solidification, you could see a lot of agglomeration. This may be because of the solidification nature that push the particle to the front and you get agglomeration. But when you try to increase the skew pressure and also keep some 400 degrees centigrade die temperature and 800 degree what is called the melt temperature, you could be able to see that a homogeneous distribution was possible with some 100 degree, 100 MPa pressure and 120 MPa pressure, 130 MPa pressure. I could see homogeneous distribution. That means, see, moment we have a solidification start, this melt, once it starts solidification, then it disengages the melt from the solid, that means die. The mode of heat transfer would be converted from conduction mode to convection mode, and it is a slow process. So during the slow process, they try to create a lot of agglomerations. But moment you have a pressure that is applied, the solid will be engaged with the die walls, and the mode of heat transfer is only the conduction mode of heat transfer, and also we're applying a negative pressure. As a result, the particle movement inside the melt will be stopped, so it would be intact with the melt. And once when you are solidifying, when it is solidifying, it's not trying to move out. So that means if you look at this pressure range 700 to 130, you could get some homogeneous distribution, and as a result, now we can also expect to have some grain size reduction possible, because you are trying to create a situation where the mode of heat transfer is conduction mode, where the grain, because it's a faster solidification, as a result, the matrix itself now has grains dimension which are in a finer domain. But whereas in the case of a conventional casting, it ranges from 10 micron to 40 micron. But in the case of a skew casting, sometimes you can see the range is from 2 micron to 14 micron. And also there is a greater improvement in the strength is also possible. And ultimate strength from some 70 MPa, it reaches to 250 MPa. So, and also the another important thing is the ductility will reduce. That's another challenge. But the thing is, the mechanical property, especially the tensile strength, keeps on increasing with respect to this processing condition. So therefore, this is another one way where, see, if you couple these skew casting also along with the stir casting, you can able to get to some good mechanical property and also good microstructure. See, the interface, as I said, it's another problem where, because the chemical reaction will induce some kind of a different phase formation at the junctions of boundary of both matrix and reinforcement. So here, the possible reactions in this case, especially when you have different material system, when you most probably we take aluminum as a matrix material and silicon carbide or boron or carbon as the reinforcement. In these cases, especially in aluminum silicon carbide, we get a different product which is called Al4C3. It's a compound. It's a compound that is formed at the junction, which is a nice precipitate around the boundaries of this particle that stops the connection between the matrix and reinforcement. And also sometimes it weakens the bonding at this junction. So because to understand, so for every case, you have some byproduct which stops the bonding between the matrix and reinforcement, and also sometimes it weakens the interfacial bonding because of the nature of the phases that are formed. So we have also extensively studied this L4C3 formation. Okay, so which is formed by aluminum and silicon carbide. Silicon carbide separates into Si and then C react with the Al and then form L4C3, and 3 silicon is left, and the 3 silicon goes into the matrix material nearby and modifies the chemical composition of the aluminum alloy also. Therefore, this separation takes place only at the surface, on the surface of silicon carbide. So L4C3 degrade the mechanical property as well as physical properties. And not only that, if you try to control this formation during your processing, sometimes in the working environment, if you have a humid condition or some kind of acidity condition, it tries to form, or kind of an elevated temperature condition, it tries to form Al4C3. So you cannot stop, you cannot avoid this. Somehow or other, one way or other, this byproduct will be formed, either during the processing condition or during the service condition. So therefore, one way to stop this degradation or Al4C3 formation is that to coat the particle. So you can coat the particle, and we have also studied this. What effect this will do on the mechanical property, whether it is creating good bonding or a kind of a worst bonding. And we have taken a silicon carbide plate, and then we try to create a bonding at a different temperature and studied the macroscopic layer here where no Al4C3 is formed, and with the detailed analysis with the EDS and mechanical property, putting this subjecting to a what is called the tensile condition. So we studied the mechanical strength at the bonding, also very, very poor bonding. It can be easily separated with a minimum load. So, and also this separation, L4C3 formation is more and more with respect to temperature. When the working temperature, melting temperature is higher, you form more amount of L4C3. As a result, it is weakening the composite system. And this formation is also experimentally demonstrated and confirmed with the XRD analysis, where you form L4C3 at the junction, at the macroscopic junction. We have also computed the diffusion length. So what length this will penetrate, this L4C3, and it would form up to 0.016 micron layer thickness. So that means it's a very fine precipitate, but the effect would be very, very adverse effect. So here it says that with increasing the working temperature, melting temperature, the amount or length of the diffusion is also high. That means you can be able to form some good thickness layers of precipitate which covers the particle. Okay, over that, as a result, the bonding is stopped, permanent bonding is stopped. So these are some macroscopic images of that, where how it establishes the bonding. And also we have done some EDS analysis to understand how the free silicon modifies the what is known as the composition of the material. So that also we have studied. And finally, so we can also study the interface formation with the micro hardness examinations. And from the interface to away from the interface, we can establish some correlation where L4C3 formation try to create more hardness at the interface. Away from that, it is decreasing. That means it's a hardness of the original material. So this X2 reactions, because the problem of the homogeneous distribution and interface bonding mechanism, that can be eliminated by developing the same reinforcements by in situ reactions. So especially in the in situ reactions, you have a gas liquid reaction, liquid solid reaction, and these two reactions are there. And especially one reaction that we have demonstrated is liquid solid reaction. That means we take a precursor solid of K2TiF6 and KBF4, and aluminum is the matrix material. And these reactions will produce TiB2 ceramic particle into it. So this is a procedure. I will skip it and I will demonstrate what is the real thing behind this in situ reactions with microstructure examinations. See, after developing these reactions inside the melt, one could see that at any temperature, whether it is 700 degrees centigrade or high temperature, I could be able to get the distribution of reinforcement homogeneous, because the particles are evolved in the what is called inside the liquid melt. So there is a homogeneity in getting the particle, and also the particle has uniform dimension homogeneously. And also we can, these are all the particles which are separated and taken examination, where you have some particle which are some spherical shaped and different shape formations are there. And so with this, we could be able to say that which gives a homogeneous distribution that can be demonstrated by measuring the hardness along the length direction, across the direction. And because the distribution is homogeneous, the hardness value measured on the surface anywhere shows the homogeneous hardness value. And also there is a greater improvement in the mechanical property. And one more important interesting thing is that we could not notice any interface formation, because the reaction itself gives the particle and further reaction may not be there. So the particle directly create contact with the matrix, and as a result it create good bonding also. So the greater improvement from the original strength of 115 megapascal to 202 megapascal, which was the greater achievement, greater improvement in the strength that is possible. And also one can imagine that it can be also extended to a mass production. But there are some challenges, as I said. See, the caster, that is very, very important. The strip casting process, and also if you try to couple these fuse casting, you have to have an instrumentation to connect these two, and also a design is necessary to overcome these challenges of the particle distribution, and also try to make an in-situ reaction that the in-situ reaction will eliminate what is known as the interfacial formation. So the science of primary processing of AMC need to be understood more thoroughly, especially factor affecting the microstructural integrity, including the agglomerations in MMC. So that is one of the challenges. But if these challenges are broken, then we have a good opportunity that there are possibility that we can make several component out of this MMC, especially the brake parts, brake liners, and also the aluminum matrix composite cylinder liner. Then we have a drive shaft that can be also made by aluminum carbon-based composites. Not only the cylinder running surfaces, as I said, brake liners and piston. So many good applications that you have with this wonderful material. But so far, this real potential of this metal matrix composite been not fully exploited. So in some of the cases, people are using this metal matrix composites with some specific processing. But for a commercial production, it still has some barrier that has to be overcome. So I think with this brief my research background, I just conclude, and then probably I can take up 2-3 questions from the participants. So thank you very much.
Thank you, Professor Balakrishna, for such a wonderful presentation. If there are any questions, some quick questions, please. Okay, probably everyone got your message loud and clear, sir. We expect next time we'll see you in person. With that, I thank you, sir, on behalf of organizers. Thanks for the nice presentation.
Thank you very much. I think I can leave now. Thank you very much.
Thank you. Okay, as Professor Bala mentioned, that automobile or the transport equipments, today morning everyone use one or the other mode of transport, which is a very critical part of our life. So to throw some light on the role of advanced composites in mass transport, now we have a panel discussion. For that, I request you all to join your hands, and let me call Mr. Sameer Agarwal, CSO, Arvind Composites. Sir, on behalf of all the audience, I request you to be the moderator for the session. And the panelist would be Dr. Ankush, from Atira. He'll be presenting the researchers side. Then we have Professor Mamta Sayyed from Nirma University. Professor Shyam Guru from Ahmedabad University. And to represent the private limited company side, we have with us distinguished Mr. Mukesh Sangvi, Managing Director, Indore Composites. May I request all of you to please join on the stage? So, sir, humble request to keep it. No, it's not required.
It's not required, okay.
Yeah. So, sir, requested 35-40 minutes. Or I'll be there. Oh, yeah. Is Mr. Mukesh Sangvi here? He was there before the tea session. Okay, he's on call. Okay, sir. Please, sir, the stage is all yours.
Yes, you can sit here closer maybe. Sure. All right. Good afternoon. It's wonderful to be here in the lovely campus of Ahmedabad University. It's always a pleasure and privilege. I'm very thankful to Dr. Ratan Singh for giving the opportunity to be able to ask few questions from a set of very distinguished panelists I have. As I was reading the invite, I noticed that I was supposed to speak to 5 PhDs in composites, and I was like, wow, feels like a setup. This conference combines participants from both academia and research side as well as industry. I come from a more commercial industry background, represent Urban Limited. We have a $50 million business which is into manufacturing of composite products, which is the reason why I know a little bit of this tech from a commercial angle. We do have different products and processes which make parts for not just mass transportation but for many, many applications. For today's discussion, obviously the topic at hand is how composites can be, what role composites play and how they can help advance the mass transportation industry. And again, for the purpose of this conversation, we can agree for mass transportation to include railway systems and buses. Because to take broader transportation, the aviation will be some set, but let's not keep that out. What I'd like to do is to really, give your thoughts on 4 or 5 themes, and making a specific one-on-one conversation. I've just lay out those themes that are probably useful, and of course, this is from a commercial lens, like I said. One is really from an application lens, right? You all, pretty much whoever has anything with composites knows that today in modern trains and buses, composites does get used for a lot of, exterior engineering parts like panels and ducts and so on and so forth. It will be interesting to hear from you if you have seen more interesting use cases of composites in the context of mass transportation, because that's the opportunity set. So that's kind of one area which we can discuss. And why composites in general is a better material of choice for many of the applications in the MT space. So that's one. The second is I'd like to get some insights from you around the materials and processes, because composites is a very wide subject, and what specific kind of combinations are useful for making these parts which we discussed, and what are the kind of limitations, because as I was kind of going through the different applications, what I realized is that, for instance, one is this whole FR property is very important, just being systems and products, and in the process of making something fire retardant to that level, you end up loading either fillers or coating, and it ends up adding weight. So that's just an example, but in general, what are the limitations of using composites in mass transportation? There's a third thing. Fourth thing is, around sustainability. And again, it's a broader topic, not just for MT application, but this gets asked many, many times. So, with your permission, I'd like to ask, what's the thinking and progress on being able to treat composites at end of life? So that's one part of it. And even as you kind of make, there are a lot of conversations around environmentally sustainable resins, how practical it is, right? And then we'll wrap up with what implications all of this has for the industry and academia. What would be your suggestion and imperative? So broadly, that's the way I thought we'll structure our next half an hour or so. So with that, let me kick this off in terms of getting you started, ma'am, on what do you see are the interesting applications in the MT sector for composites? Some of it which has been already established and the ones which are more emerging and new.
Good morning, everyone. I suppose I am audible up to then.
Yeah, you are
Yes, I will try because I have that habit because my students are always picking up the last benches. So yes, thanks for the question. Very interesting to discuss upon mass transportation because it is according to me. I will come back to your question after giving some prior this that composite, as we all know, is a very wonderful material. Strength to weight ratio, then the manufacturability and material selection, material availability. All these things are very wonderful for composite because we can make a tailor-made material and we can use it. So the advantages are lots of. At the same time, we have some challenges and we also have some disadvantages and we also have some responsibility with composite. So according to me, if we go for the some applications, there are lots of applications, locomotives and our bus. There are even a large part and a small parts. Challenges are with both large and small. So we also have to cater the need of both the parts, if it is a large part or a small part. I am not specifying any part over here, but the thing is that there are two main challenges. I will come up to the main challenges we are facing composite. One is the safety aspects, and second is the recycle, and third I would also say the scalability. Because many times what happens that safety, according to me, safety comes first in the mass transportation because there are fire safety is we have to take care because this material is highly combustible and the flammability is high, and at the same time it's leaking also. So in mass transportation we have to take the safety aspects first, and second is the recycle because as it is a mass transport, we are using the material also in mass, and after a period of time, it has to be recycled, and that is why the lots of research is needed to be done. And for the third challenge is in the research that whenever we are going for the research, this material is somewhat we all know that it is few decades older. I may say that it is very young material. So we get very less prior art or very less historical data, and because of that, doing the research, there are certain challenges. Another thing is for researching, we need some infrastructure, and that is also kind of a challenge. But altogether, if we do and if we come up with the solutions, then definitely people can do better in mass transportation. But still, there is a lot to go for doing all these things. So that is what my views on this mass transportation, composites in mass transportation.
Thank you. Koji, why don't you go next? As rightly ma'am says, that there is a role of the advanced composite in the mass transport. So about the transport sector, that is the transportation of the transportation from the conventional material to the advanced composite material, where the role of advanced composite material is not only the material choice, but apart from that, it is a strategic asset where we have to be see that how we can design, we can build the material for all operative or the vehicle operative, including roadways, railways, aerospace, maritime, and India, this particularly composite industry, they are doing very well. If you say that the last 3 to 4 years, 5 years, that were having also mass transportation, the Vande Bharat that already is there, being made in India. So where now we are just come up with a certain, these are the opportunities that we can say that we are Indian composite is targeting. Apart from the opportunity, there are still challenges that from these 2 days already we are talking about the cost and the availability of the raw material, which is very much important. These are the 2 crucial challenges that we need to be cover up, to come up with a proper solution for that. So already the Meta is now making the carbon fiber, which can be the maybe in the future after 5 or couple of years that can be one of the major user of this particularly carbon fiber in the mass transportation. These are the things that we have to work out on that. So with that, I can say that these are the in the advanced composite. There are opportunities. Parallelly, there are challenges that we need to come up with that. Of course. So, Prashant, you can share general remarks also, but specifically want to build upon the aspect of safety, which in my mind is a very crucial element in the mass transport application, because you're talking of something which is a day-to-day for a large number of people. You could just kind of share your thoughts on that.
Yeah, I mean, I will come to that. I'll just try to bring another question, for rail transport and all these. So I'm trying to bring a little bit of aerospace applications where the composite is, and let's say 20 years back it was used to some extent. If we see today, they are claiming full aircraft is now composite. Now, what is happening in these 20 years? So every component of the aircraft is now composite. So every landing gear or anything inside the wing or something is replaced with composite. That's not happening if we come to, let's say, automotive sector. We're still sticking up with the more of a superstructure kind of thing. And what I see is, as I'm pointing, this material is a little bit new. We don't understand it fully. So what we are trying to do is take the metal processes, you start with manufacture, all the design processes for metals, and try to replicate it when it comes to composite. So providing the holes and how you clamp and all those small processes, we're simply borrowing from the metal. Metal is very mature with the data, experimental data and everything. Composite is very not there yet. And that is, I think, stopping us from using this material at a critical component. Aircraft industry, they spend enormous resources to study this material's use for a critical. Their data doesn't get published outside; it's not available. So what I see is most of the automotive industry, for example, in the previous talk, metal matrix composite, it's a beautiful material, but it's not yet used enough. So these industries, they have their own data. It's not yet for everybody. There is no standard, especially when it comes to composite. And I think that is stopping us to go for a critical thing. And I think when we start using everywhere, like in shaft and everywhere, where we actually get much of the weight reduction, and I think That's what I see a stopping. Coming to safety, yes, I mean, we have to composite with coating and what kind of ingredient we use in the say, still need.
Very interesting, very interesting. So, what I'm hearing is that there is a set of technologies and solutions which exist in the aerospace domain in terms of applications. And if only some of those were to be able to trickle down and flow into automotive and transportation, there could be a much bigger adoption of composites. Is that the main point you make? So, I mean, from the commercial side, so I have to ask you, you guys have been in empty space for a long time as well. So from a commercial point of view, where do you see the use of composites in the mass transportation sector, broadly speaking?
So, let me just touch base on 2 points here. First thing is, as you rightly indicated, the commercial part. So, when we talk about the penetration of composites in any of the mass transport applications, what shows stopper there are two showstoppers basically today. First thing is the commercial, because it always boils down to piece of kg for your composite application, which is going on to your public transport in the form of railways or metros or buses. And that's where the challenging part is, wherein cutting down the cost by even 50 paisa per kg or even 1 rupee per kg is going to be valuable. So that is what we are looking at when we discuss the entire domain of mass transport. And the second part I would like to touch base is the sustainability part. I think in your initial introduction you mentioned the sustainability part also. So somebody yesterday mentioned very pertinently that what would be the best F1 car design. The guy said that once the car crosses the final line, it should get dismantled and go back on the shelf to get reused. So that is what sustainability is going to be. So currently we are looking at India standing at 0.4 kg per capita of composites. US stands at 14 kgs. But looking at the quantum of population we have versus what they have, even 2% penetration would equivalently match the amount of composite getting used in India. So we see the cause of concern in this whole application domain is the end of life cycle concerns. Because even if that 2% penetration of composite happens in India, kgs I would say, you would be equivalently seeing composites everywhere around, or today we don't see. So end of life cycle is what is going to be the sustainability is going to be the challenge moving here on. So yesterday we had a discussion on microwave technologies causing the disintegration of the finished goods, splitting them into composite resins and glass fabric and all that. So more of such technologies would be required to be brought into each and every domain. You're seeing windmill sector getting these technologies from Arvind, I would say Aditya Birla. They have a system to dissolve the epoxy in the glass fiber and separate it. Such should be the penetration in each and every segment of composite, because the end of life cycle is going to be a concern. You implement composites today, but what after 10-15 years when the thing gets disintegrated? You have a heap of composites sitting around you, and then you start thinking what to do about it, as it happened in the US for the windmill sector. So that's going to be one showstopper or maybe a roadblock which people will cater as far as absorption or usage of more and more composites in automotive and mass transport is concerned. So commercial is one, of course, because our L1 philosophy somewhere hits us at every point in time. So every organization, may it be a metro in a tier 1 city or a tier 2 city, every design is different, every safety standard is different. They have, somewhere we have phenolic prepregs, we have polyester resins, but you have the standards. You have EN 45545, HL1, HL2, HL3 taking care of your safety standards. So on safety you are covered, on design you are largely covered because there are experts in Alstom, Bombardier, Titagarh, which these guys have evolved designs over the period. So these two facets from my angle are pretty much well covered. What is not covered is the commercial part. Second is the sustainability part. That's what I would like to sum it up.
All right, thank you. That's a very succinct kind of description of where we are in terms of challenges. One other topic which comes to mind is this whole repairability. Right? that's always a question mark. So, any of you would like to kind of weigh in on how far we have come in terms of being able to repair structures or components or parts that are made of different kinds of composites? Because there's always a concern that, composite part has to be practically thrown out and replaced as it is. And even the replacement process is not as straightforward and simple as the metalworking is. So, any thoughts on repairability of composites, especially in the context of MT? Yeah, please.
If we are talking about the mass transportation repairability of the parts, I would say that it is very challenging, because all the time you have to inspect the part, because you cannot take it out every time, because the part is large size, and you cannot take it out every time. You have to repair on the spot or on the site. So that is the first challenge, that inspection. The inspection is must. No cracks, no any other damage or anything, advantage or anything. And all the time you have to inspect this, and then you need to. So for this repairing, you need the skilled person. So that is another challenge, that you all the time go on repairing, go on inspecting and go on repairing. That is a very challenging part, and that is what my views on the transportation repair, which are used in transportation.
That's a very interesting part of repairs. It's what at least I have come across. We typically see toilet modules in an ICF coach. I think people travel here day in day out by railways. So you see those FRP components in the toilet modules, which are 4 in number per bogie, right? So typically when the part is new, it looks very good. The train runs for 1 or 2 years. You start screwing metal strips on top of it, or having some metallic fragments on top of it. We have come across this situation many times. It starts looking really bad after, say, X number of years, after which the part has come under use. So that is where composites material can help us. Some trained professionals sitting at that repair facility or ICF or RCF, wherever the coaches are getting refurbished or repaired. So a skilled task force who has fabricated the bogie or the toilet module, a makeshift repair will only look shoddy, I would say. It will not look aesthetic. The aesthetic value is one. So that is one thing. Second thing is, during the transit, say I have prepared a metro interior coach, and it's getting transport from one location to site. So during transit, there are a lot of damages which take place. We have witnessed that many a times. So we have to station a next set of manpower at the facility, where there are experienced guys who do the repairs and do all the producing before the installation of the contents onto a rail coach or a bogie or metro interiors. So that is second aspect of the repair. So both have to be catered, where the crux is you have a skilled manpower sitting there, who's well known to the process, the curing pattern, the looks, the aesthetic, the colors. So those are the guys who will be able to create that difference, even for a used part or a new part.
See, this is typical example of how metal and composite are differing. So if you talk about metal, come back to phrase in a minute, but if you talk about automotive, for example, we provide a lot of holes and so that some other part comes in and attach it. And the whole concept of repair is component based. So something goes wrong, then you take it out, you put it back again. That's how you go on. I'm talking about component, not just the surface that is damaged. We're talking about surface because of about the superstructure. But let's say if I use composite everywhere, then there is a different way we need to think. So if we think in a metal way, then we provide all these fastener locations. And this material is typically bad for providing fasteners. Inherently, this material is bad. Eventually, these fastener holes will deteriorate, and you will loosen out, and then it will have different implication on the component, and it will get damaged. So I think what we need to do is the entire manufacturing has to undergo a change. So that has a big implication on the whole industry. Like now it is like supplying small components in supplying. But when we use composite, I think that approach may need to be changed or questioned. Like, can we have an integrated thing? Don't have to put together these things. It's challenging because making the whole thing integrated is again a difficult task. But there may be some way we can come up with attaching these parts in a different way rather than just with fasteners. It equally applies to aerospace industry or train industry. You use fasteners. Goes there, like how we can go to kind of constructions.
Totally, very interesting point you're bringing again, that we tend to extrapolate our thinking around manufacturing from the metal world, right? Which is why, especially in mass transport, what I've seen is that you create a FRP component, a carbon component, which is, let's say, 100 rupees, and the fastener which is supplied on that may be like 300 rupees, right? So, in essence, we have locked ourselves in the thought process which is inherent with a metalworking domain. So, building on that, one question I have is around, in terms of getting some tips and directions for the industry participants. Majority of the Indian industry is built upon basic processes like and molding, and some degree of RDM and other infusion processes. Right? So, when it comes to the mass transport sector, the applications are technically where they are possible. Would you have any advice or pointers around what kind of capabilities the industry should focus on acquiring or refining, right? So that your composites can play a bigger role in the mass transport industry? Like manufacturing point of view, always the process is better. Like the complete performance of the composite will depend upon the what method you are adopting to manufacture the composite. Right. So, say for example, the majority of the components are like either being made from the dry fiber and then the other process that can be adopted like hand layup or vacuum infusion process. However, there is enough literature available on the comparative analysis of the different manufacturing processes. As far as the mass transportation, like we talked about, so here I can say the processability timing, that is also very much important, where like in a short period of time that maximum can be done. So pulverization is obviously one of the method. Pre-pack, that now the people are also adopting the pre of the mass transportation components. So these are the few processes where this kind of can. So that is my submission on that.
Maybe picking up from what Shyam just said, the monocoque design aspect, I mean, your tooling and then your mold making is the process where you could maximize the square meter of your area, which is part of your design. So if that design is intrinsic enough to ensure that your mold without having too much of attachments, or so your mold is going to get to either your hand or your process or wherever. The larger the mold, or the designer who sits over there can cover maximum square meters of area in that one mold. That is the time when we will be able to have least manufacturing time, because you are creating a module or that frame out of maximum 2 or 3 molds. So your tooling team and the designing team probably has to be equally responsive of creating a design which will result into a faster production time.
3D printing. That's the action. 3D printing.
Ask you all if there is a additive manufacturing concept which has gotten into composite domain. Any update on that? What's happening called composites? I'm personally not familiar, but I would imagine that some of you have heard of it at least. Or
As far as today developments, we have now layup that we can put together, and as some presentation showed in the houses. So the scale with which you can do is there. How much control you have on the property at the level that is something we're not sure. Like if you want to use, let's say, for structural application, where you are subjecting the application to really loads like fatigue and all, what control you have. So if we talk about, let's say, talking 3D printing for houses, that is possible for the train, the whole structure. Possible with all sorts of things arranged in one go, and the entire setup is done with 3D printing. Then it would be fine. I mean, like you have less maintaining issue, carrying and make that with even if possible to mass produce. But when it comes to structural applications, I think 3D printing is not yet there. With, like what we design, what we can get out of 3D printing, I think we are not there. I think.
Even though in that in not in India but in other countries that the 3D printing are also adapted to prepare the or to manufacture the tool. So basically, like what the time is taken, lead time is taken by the manufacturer that need metal. So the 3D printing can reduce the time for the tool manufacturer for the to make the component from the hand lab process, not for the process, but yeah, that is for the hand lab process. It can be is one way that where the people are working. Certainly, the tooling using the 3D printing process to make tooling is definitely a good use case. I'm sorry,
I would suggest industry that they should give more time in designing and design of according to me some parts rather than larger, and because always the larger parts have the curing problems once you than when you are making the parts while manufacturing, and these smaller parts can be as are suggested should be attached in some unique way, and if in that way we are going to design the this problem would be, I think, would be rather solved. And the other thing which I agree with is that always we are trying to replace the part, and we are not making unique applicability of that particular composite. The design should be very unique, and it should not be for the replacement of the part, that you are replacing any wood or you replacing metal or something like that. It should be a unique application for that composite part, and it should be designed in that certain way. So perhaps the problem could be solved.
so we had a good round of inputs. And just attempt to summarize this a little bit. What I heard is that the good news is that there is a big potential for enhanced role of composites in the mass transportation sector, different applications. There are challenges in terms of its commercial attractiveness, in terms of safety, in terms of durability, in terms of design, in terms of fire retardants. But good news is that all those potential challenges, there exists solutions which have been tried, tested, and proven to be adequate. It's certain aspects may not be as widely present. So, for instance, durability, people are saying that you need to have skill craftsmen can actually invent, but there. So one set of conclusion is around the fact that there is a very bright potential and challenges which are there. There exist solutions. Right? The other aspect which Professor Sham brought was to try and understand what's happening in the aerospace world. So there are lots of technologies and methods which have been developed, which in a way take a look at using composites as a material fundamentally different, trying to part-to-part replacement, especially in context of assembly and manufacturing. What we discussed is that stop thinking of fasteners as the only way. In fact, fasteners is a bad way to put together composites. A more elegant solution to reimagine the manufacturing itself, perhaps along the lines of monocoque structures, where you're replacing multiple small parts which are fastened together with larger, more complex monocoque type platforms, which obviously will require more complex designing and tooling, but that's very much here and available with computation and other things available in the design industry. So I would say those two, I think, sets of insights came out very loud and clear. Any closing comments from any of you before we kind of wrap this up?
We'll talk about the regulation framework. So that is one of the essential parameter for the qualification of the material. Still, like we are adopting the European standard that EN 4154, but still, like there is need to be developed the Indian standard where the industry should closely work with the this guys, like with them they can develop at least the Indian standard where the Indian, as per the Indian environment and the safety parameter can be designed. So this is one thing that where the master should allow.
Good point. Yeah.
No, I really agree with Ankush. I mean, it's really something which is necessary, like building on standards. Very small nitty-gritties need to be brought under the scanner. I agree.
We've seen evolution of these standards coming into the Indian context as in how the penetration has increased. So when we talk about BIS, they are largely a subset or kind of evolved out of European standards and ASTM standards. So that was directly, the journey was linked with the amount of penetration and the application which is seen around us. Right. So the same is with mass transport. We follow EN standards because that's what is valid today. The more metros come into cities, tier 1, tier 2, the application grows. That's where the approval agencies are coming into the picture. And that's when we start evolving towards our own standards. So it is a matter of time when it comes into context.
That use more composite will have more solutions with experience.
Any last words from you?
It's what she said. I mean, use more.
All right. So with that, we session and thank you very much for being a patient audience. Thank you and may
Any questions from audience? Okay. Yeah, please.
I don't have a big question. I have a quick comment on whatever what I heard. So mass transportation actually requires some mass production as well in line with that. That mass production actually requires mass customization because not every product is going in the same way. Just an example, if I consider aircraft as a mass transport, the seating arrangement, we are saying 250 seats in an aircraft, but most of the seats are very unique in dimension. Even 2 inch are different, 1 inch is different. You have to produce entirely a different set of product. So that mass customization is most essential thing. Otherwise, you will be never doing that kind of product anywhere because the tools will be different. For every inch, you have to have a different tools. That is another story. And materials and process is the key to entire thing. Design is of course, but we have to go into thermoplastics. For very quick production, mass customization, as well as for recycling. And India has to come up because we have so many polymer manufacturing. I mean, we ourselves, Reliance is doing a lot of stuff. Have to include glass and polymer or carbonate polymer, not necessarily P and T, but we can do DP and P. So that's just a comment.
Thank you.
Yes, I mean, sorry to add this. There's a very different philosophy when it comes to metro applications in India. Bangalore metro has to look different. Pune metro has to look different. Mumbai metro has to look different. It's like one part fitting into multiple metros is something what MMRDA or the manufacturers have to look at. But everybody wants their own designs to come up. That's where customization slightly takes a hit. So that's the only.
Thank you for the input. Okay, thanks. Just a moment, so please hold on. So with that, thanks for the fruitful discussion as well as the key inputs for all the audience present here. Now may I request Professor Sunil Kale to felicitate our moderator, sir, Mr. Samir Agarwal. And Professor Mamta Sayyed, please. Dr. R.K. Singh, please. Thank you, sir. Thank you, Sunil, sir. I request Dr. R.K. Singh to please felicitate Mr. Ankush Sharma. My bad. Professor Shyam. May I request Professor Bimal Roy to please felicitate Mr. Rahul Ranade from Reliance Composites. And on behalf of all the organizers and audience, I thank all the panelists and moderators, sir, for such a fruitful discussion. Thank you. Thank you, sir. You can please have your seats. Okay, can we have a group photograph, sir, please?
He's already taken that opportunity.
I don't know, he just mentioned. Okay, please make it quick.
Thank you.
Okay, in between the lunch and the ending of this, we have a presentation by Mr. Krish Munim, business head, AM Lubricants and Coating, and he'll be presenting what all they are having for release agents.
Hi everyone, good afternoon. I realized on the last presentation before lunch, so I'll wrap up within 15 minutes. Don't worry. Thank you. So I'd just like to start by thanking Dr. R.K. Singh and the organizers and the university for organizing this event. It's been wonderful so far and for giving us this opportunity to present our company. So my name is Krish Munim. I look after the business, the sales and the operations at AM Lubricants and Coating. Our brand for release agents for composites is Sliplease. So over the last day or so, we've seen, I think, very clear themes emerge from the discussions we've had so far. That's primarily innovation and more on the academic side, the latest research trends in India. And we've seen the challenges that are facing our industry and what we need to do to overcome that. That's mostly on the raw material side, on the development side, and of course what's been discussed today, which is too much for me to summarize. But I'll try and stick to these two themes while I'm presenting our company. So just to give you a brief on what we do. We've been manufacturing mold release for around 22 years, and we're the only company in India that's solely dedicated to developing and manufacturing mold release. So we started in the rubber industry about 22 years ago, and about 10 or 12 years ago, we diversified into polyurethane and into composites. Our manufacturing facility is in Nasik in Maharashtra, and we have our sales offices in Bombay. From there, our products, Sliplease especially, is exported to 24 countries, primarily into China and into APAC, and we've just started our sales into Europe and into the US. We pride ourselves on manufacturing and developing all these products here in India and locally sourcing our raw materials, giving our industry the chance to develop faster and have these raw materials available locally. This is our manufacturing plant in Nasik as well as our R&D center, and we have offices in Bombay and in China. As I said, we export worldwide. Our latest development is in Germany with a partner where we plan to locally blend our products and sell in that market. Just a little bit more about our production facility. We have a 5,000 metric ton per annum production capacity, which includes water-based and solvent-based products. This R&D facility, which is it's a state-of-the-art R&D facility, which is completely equipped for even testing. Like you can see the vacuum infusion process, where we have a dedicated space purely to test and to validate our products with our customers' manufacturing methods. We plan to invest and expand our R&D space over the next 3 years to almost quadruple the current capacity. For quality assurance and our manufacturing validation, of course, we have a standard lab with access to all kinds of machines. Now I'll delve a little more into our product line and also focus on the innovations that we have for the industry, since that's a very important theme in how we are developing our products here in India to not just match what you find in Europe or from abroad, but we are in fact 1 or 2 steps ahead. So I'll start with the most important, our mold release agents for molding, whether that's the hand layup process, the vacuum infusion process, or the RTM process. The industry standard right now is for people to use a sealer and a releaser. What our R&D team has worked tirelessly to develop is a combined product where you get the benefits of a sealer and a releaser. So sealing your mold porosity, as well as the formation of a semi-permanent film that allows for easy demolding. So rather than you applying 6 different coats using 2 different products, we've combined that into one product that you can use much faster. More importantly, I think this is more applicable to your larger sort of molds like wind or maybe train and bus bodies. But we have a far reduced odor and much fewer emissions, which makes our product far more sustainable and creates a much better working environment for our customers. I think what we've seen in the wind industry so far with our competitors' material is you find a very strong smell that requires gas masks and at times to even vacate the room. But with our product, this is greatly reduced and worker safety is also enhanced. And this combined product, of course, doesn't compromise on any of the existing requirements of the industry, whether that's gloss, whether that's your room temperature curing, and works with a variety of resins as well. We have this available both in solvent-based and in water-based, which I will talk about in the next few slides. So, of course, we have this product for all the basic applications of hand layup. You can just have a look at the pictures and yeah, these are most of the products that we supply to. So if I focus on the water-based grades, this is a new development, not something that you see too often in the molding industry. We are working with a few customers in India, and in fact, this reminds me of a point that was brought up in yesterday's panel discussion. I think that Dr. Chauhan brought up that, for these new developments, many private companies don't feel like experimenting. They don't have the time or the resources to dedicate to the development of new products. So of course, we're always very happy to work with academic institutions. But for the development of products like this, which you don't have available in countries outside India, we need more engagement from our customers, because there's only so much that you can simulate in a lab. And with the ever-evolving or changing manufacturing capabilities, the only way to test these products is to do it in an actual manufacturing setup. So, if you're interested in these products, we're very willing to work to try and improve these products. Our latest sort of development is Sliplease 1612W. We realized that the thermal stability required is a lot higher than the first iteration of the product at 120 degrees. We needed it to go up to 180 degrees for a much longer time, which is why we developed that product, which we could only find out by actually testing at our customer's end. So I strongly encourage that people try new products to help development. So we have water-based and solvent-based grades for the vacuum infusion process as well, and for marine applications. The same hybrid grade, which would combine the sealer and the releaser, is used for the RTM process as well. We found some good success with that application. This brings us to the pultrusion segment. So of course, this is a completely different range of products, but we have some interesting developments here too. So our standard product, which is used for your regular pultrusion, is 6287D. Our latest development is 6440B with improved lubricity and is targeted at your thinner, more complex profile of parts. So I think this is below 3 mm. We've seen this requirement growing considerably in the Indian market, and we don't yet have a local product that can tackle this, which we feel we now have. And is a very impressive development. This is another interesting development that we have. I don't know if you can see the grade name down here, Simply 6133. So we have a water-based grade for sheet molding compounds as well that is deliverable through an aerosol can. So in the more complex parts where you would generally be using bulk solvent-based release agents, it's difficult to spray or to wipe the sort of corners of the mold and train your workforce to make sure that you do it every time. But we're the only release agent company that delivers these release agents through an aerosol can. And that allows, of course, for far more efficient usage, and it's a lot easier to train workforces that are more used to using aerosol cans rather than using bulk material or adding spray guns to your manufacturing setup. For filament winding, we have standard mandrel external release agents. These are currently solvent-based, but we are working towards water-based release agents in this field as well. And actually, this is a particularly interesting application that we've been seeing growing in the Gujarat market as well as the Northwest, where we have found some success with our water-based release agents. And we feel this is a great opportunity for people who want to work towards a more greener, sustainable manufacturing process to try our product here. In fact, this is how we realized that we needed to increase our thermal stability, because a lot of the molding process here involves higher temperatures for longer periods. So this would be a very interesting avenue to work on water-based release agents. In the electrical application, we have both for higher thermal stability and for cold molding as well. Primarily, I think the industry uses epoxy resin here, so it's mostly catered towards that. The key benefit of our product is that it doesn't leave any white marks regardless of the temperature of the mold and for how long these transformers are molded for. And one of our newest applications is for optical fibers. I think this market is also considerably growing, not just in India, but in the neighboring countries as well, especially to cater to the more developing nations in Africa and Southeast Asia. So we've got a product line for this as well, which has been quite successful so far in the Indian market. That's it from me. Thank you. If you have any questions, you can.
Any quick questions from the audience?
Maybe just one question. What do you think is the drive to convert all these release agents from solvent-based to water-based? What's the drive?
So I would say there's two drivers. Number one, just for safer working conditions. Obviously, having solvents in your factory is extremely hazardous. If there's any risk of a spark, most of these solvents have a flash point between 40 and 50 degrees. If there's a single spark, of course, that that would require people to start training their forces in fire safety, dealing with these solvent-based release agents. And the second driver is most likely from your customers' end. So if you're a molder, they would want you to have a more green, sustainable manufacturing process. At least that's what we see in most of the industries we cater to. I would say especially in automotive, railway parts, there's a big drive towards water-based, fewer emissions. So yeah, I would say these two drivers.
Actually, is it beneficial if you change from solvent to water? That makes it more commercially viable.
It's actually twofold. So yes, water is cheaper than solvents, but to develop a water-based grade and to have it consistent is far more difficult because your base active ingredients completely change. So it depends. You have to spend a lot on R&D, but yes, your cost will decrease. You can export easier. There is a benefit for sure.
How is AM difficult in linked?
They're not linked.
They're not.
No.
Because your bottle was showing manufactured by McNew.
Oh, sorry. No, they're different companies. Any other questions?
Okay, in that case, thank you, Mr. Rahul, for such a crisp and informative session on the release agents. Now, may I request Professor Akhand Rai to felicitate Mr. Rahul Ranade. Sorry. Oh, sorry, Krish Munim. Yeah, my bad. Yeah. My apologies, is Mr. Krish Munim, business head, AM Lubricant. So with this, we come to the ending of this first half of session. Now we'll break out for a quick lunch, and may I request you to be assembled back here in 45 minutes time. So we'll attempt to start on time again at around 2:15. Thank you. And the venue remains the same. The yesterday's place, UC building, room number 107 and 110. Enjoy your lunch.
Welcome back, everyone. Our next session is on application of composites in disability products, presented by Professor Sam Gurau, who is one of the professor at Ahmedabad University teaching practice of applied sciences, and he has founded a startup that works for developing innovative products for disabled people. Over to you, Professor Sam Gurau.
Yes.
Good afternoon. As was explained, I have a startup. I'm a faculty at Ahmedabad University, and I founded this startup, Jago Motion. Its aim is to provide mobility solutions for disabled people. So our aim is to basically reach every disabled person in the world. Its startup is in a small town in Maharashtra, Sangli. We did it with the aim that we can create employment for other than the metropolitan cities. It's a challenge. I will bring all the challenges that I face as a startup and as a technology. Our aim is to provide solutions for disabled people in the form of mobility solutions. Those solutions should be affordable to disabled people, and our aim is to create employment for disabled people by means of those solutions. Just to give you, many of us have seen disability in one form or another at their home or outside nearby. I mean, I have seen it firsthand with my mother. I mean, my mother was paralyzed and I was with her, and that was the moment of enlightenment for me, that there was no solution appropriate, for her, and then I could give her a good time in her last years, and that was the time I thought that something needs to be done. That doesn't mean that there is nobody who is doing anything. There are people, there are a lot of NGOs, there are a lot of companies who are doing a lot of work, but it's still not enough. Just to give you an idea on what disability is, still I want to touch. So disability, it can happen at birth, like cerebral palsy and different types of diseases with ear, eyes, or the physical disabilities. Then old age is everybody connects to. Old age, like these days, diabetes and other reasons are becoming very, very prominent. Paralysis is becoming very common. Then accidents. Everybody knows the traffic, and we crib about accidents, every day. So accidents is a big thing, and especially because the young generation gets affected by accidents. They have to live many years, and they get affected in the early age. They don't know how to go in this very turbulent traffic. And of course, diseases, other than these diseases, there are other diseases. The people need to go through amputation. I spoke to many people. I mean, I saw in my home, I saw neighbors, I spoke to firsthand. Last 4 years I've been working. But 4 years, very consciously I was meeting people, talking to them. What I saw is their mobility is restricted, so they don't move. They're at the home. They're not going out. They're not going to the social things. They're not going to the parties, events. They're restricted. People are also they don't feel shame in leaving them at home. They themselves don't feel that they need to go out. So the mobility of disabled people is severely restricted. And this is influencing their expected lifespan. So people who get severely affected by disability, their life comes down drastically. I mean, somebody who gets a paralysis survives, my mother survived, I think, 7 years by doing a lot of efforts. I've seen people surviving 10 years at max, I mean, I'm not claiming anything. Please don't misunderstand me. This is a general data which I collected and trying to interpret it. So my finding is mobility is at the heart of their life expectancy. They need to be mobile, they need to move out, and that's where I decided to, target, work on. So just to give you some data on what kind of disability happens due to what cause. So you just see the numbers there, and these are not really well accounted. The list that I get from the district administration is even not more than 20%. 80% are unaccounted people who are getting amputations and so many diseases and gangrene and so on. So the accounted data is this, and which is quite significant, contrary to the solutions available. So if you see 5.4 million leg amputees, every year about 1 lakh leg amputations, cerebral palsy, 3 out of 1,000 newborns. I mean, polio, we are fortunate to, overcome it significantly, but we still have to look at other things. Arthritis is one of the common accidents, as I said, spinal cord. I mean, a lot of working professionals, they're facing difficulties with back injuries, and then it's slowly going down to hip bones, knees, so they're not able to walk. Eventually, they give up on their job. So it's happening. So it's coming to your doorstep, it's because of the work environment we live in, the pressure that we live in, and the unhealthy food and the exercise and the many things. But the effect is that this number is growing. The gap that I see is there are a lot of NGOs in India, and I'm really grateful to them as a disability partner that they're doing fantastic. I mean, I will talk about some companies who are doing great work, but there are so many NGOs. Government is putting a lot of money. It's not that government is doing nothing. Government is doing a lot of things. So where there is a lack of reaching out to disabled people, there are companies also. So what I found is NGOs, they usually tap the CSR funding. Then money is distributed in some existing solutions, and that reaches to disabled people in whatever the company produces. So there is no drive. The company is not directly connecting to the customer here. So if we're talking about a cell phone, if somebody has to innovate a cell phone, he has to worry about the customer, like what customer wants and how my cell phone will be sold as compared to other 10. That doesn't happen when it comes to disability solutions. Companies which are providing these solutions, they are providing it mostly through NGOs or government or CSR. So whatever they have, whatever their limited understanding, of course they work 20, 30 years, but I still call it a limited understanding because a lot of research has to happen in this sector, which doesn't happen. They supply it, and the NGOs, which are the in-between party to disability and these companies, they simply take these solutions and provide it. And the disabled people, they get it mostly free. So they are kind of, feeling great about it. I mean, they're not complaining. They're not in position to complain. They're simply accepting what is coming to them as something, gift, which is not true. That's not the aim of the government. And that's where the gap. So this gap needs to be bridged. So somebody has to act like an NGO as well as company as well as, tying up these governments. So this is a huge gap where somebody has to work. And I'm trying to I'm a small, very, very, very tiny micro startup. So this year we're launching our products, just prototypes. So I'm expecting many more startups will come and work in this gap. Second gap which I see is cost versus functionality. So one side, there are beautiful innovations from Europe and US because people afford it. Functionality is better. For example, exoskeleton easily costs more than 3 lakhs, 5 lakhs. In India, it's only people can afford it. In Europe, probably it's a solution that can be easily brought in market, but in India, the moment functionality goes up, the cost also goes up and it doesn't become affordable. So affordability versus functionality and cost is a equation that we need to work on, and a lot of innovation is required. I mean, many of these NGOs, they import things and that causes this cost to go up. So a lot of innovation, there is a scope for innovation. And I'm not talking just a prosthetics or a vehicle, I'm talking in every sector, like eyes, ears, every form of disability. There is a tremendous scope of innovation. And isolated products, I thought, many more startups, I mean, startups take one solution and they go and they face, this is more from a startup point of view, that they face the challenge of, bringing that product and then they get copied by existing players and they don't survive. So startups doing innovations, they're not surviving. So very limited number of startups are entering in this domain because manufacturing intensive. Understanding the customer is a very complex thing here. It's not a very straightforward customer. So somehow startups should come together or somebody should take effort in getting these solutions and sell them under one umbrella. Like a DMart for disability, something like that. So I'm trying to think in this direction. So this is a sort of portfolio we are building. I mean, I will not be able to spend too much of time on showing all these things. I'll just give you a glimpse. Rather, I would like to spend putting things as a challenge, what challenge startups and particularly this sector faces. And then I will end my talk. And then as a faculty of Ahmedabad University, I have this is a composite conference, so I would like to, touch on the composite program that we have. So this is a portfolio we have. So we have electric wheelchairs, different types of walkers, and the prosthetics. So we are working on these things. As this is all we are talking about composites, I am also 20 years in aerospace industry, and I worked a lot on composites, design, analysis, and a little bit of manufacturing in aerospace, but now I'm doing it. So I'm trying to bring composite to all of these products. So making lighter is one thing, making cheaper is another, but to be frank, I must share with you, it's not easy, because going with metal, mass production is much easy, outsourcing is much easy, whereas with composite, it's very difficult. If you're developing something and you want to scale it up, it's very difficult. Because if you're talking of number like 1,000, 10,000, it's still very difficult. In the early phase also it's very difficult because you spend a lot of money on the mold. But composite has an advantage which I saw is when you are in the early phase of an innovation, doing a lot of trial and error, you can use composite. So you can try out with composites. Okay, so there are advantages and disadvantages of composite when it comes to small scale applications. I'm just showing few we started with in last 3 years, and these all applications evolved simply upon the request of customers. I mean, I don't innovate something sitting in a isolated place. I talk to people, I meet people, what they need, I develop it. And it's just a customizable solutions that I build. For example, we build a tricycle and we want to make people employable with this solution. So like Swiggy, Zomato, we can provide the vehicle which is electric. All of these are EVs, first three. So it's easily available thing. Then second one, you see a different form of wheelchair. I saw wheelchair, I spoke to people, why don't they use wheelchairs? There are so many wheelchairs available. Then they say wheelchair simply tags us. It identifies us as disabled. The moment we sit in the wheelchair, we become differentiated from the normal people. We want to be normal. So something which looks normal. So our products are evolving toward needs of disabled people. So we have done several products now. One thing which I want to focus today for next 5 to 10 minutes on the prosthetics or the limbs. So this we started as I'm an academician. When I started, I literally knew nothing. This is what I want to share with some young people if they are there to do a startup. I literally knew nothing. I mean, I did a lot of work for aerospace industry. I'm expert in design and analysis, but did a lot of problems, very complex problems. But when it comes to nitty-gritties, building things, we really lack the confidence and things. So I built the first leg 10 kilos, which I can only carry on my shoulders, I mean, to laugh about it. But then eventually I built something which is 1.5 kilos. And I'm happy with the way I build a prosthetic which is, can be made in a day. I did not use any mold. I have developed my own manufacturing technology which avoids using mold. I have tried it for even a dialysis machine in Bangalore. Not a single mold was used. That technology I want to evolve, but then 3D printing has come. And I think, this is a competition. But then while working on this product, something came to me as a different understanding. So I would share it with you. I just put few companies in the market who are leaders in disability. They are selling wheelchairs, food, arm, many things. Ottobock, German company, one of the best. Alinco is Indian company, doing a lot, doing great job, supplying to many people. InstaLimb is, you just book your place on the website and you get prosthetics supplied to you at home. So there are many, a big list is there, fortunately. And just listed below a couple of Jaipur Food and Narayan Sansthan, they are giving food for free, artificial limbs, leg cut below knee or above knee. I mean, I wouldn't say, behind the rest of the technology these people have, but they have taken this technology last 30, 40 years. So hats off to them, the work they have done. But now time has come to think beyond. I'm just showing few and then I will put light on what I'm thinking. So this is a kind of, you see, general food or prosthetics given to people who do not have legs. These are variants where this is something below the knee, ankle, below the knee, then completely above the knee, the full prosthetics. This is not our products, but I put it for reference. Then there is the next thing, exoskeletons, which is basically initially thought that only for people who have legs, but they don't have probably sufficient strength in their legs, like a polio person or a paralyzed person or an elderly person who cannot walk. Only those people can wear this, which is not true. I'm coming to that. But exoskeleton is a solution, alternative to the prosthetics. And then implants. Implants is another which is, growing now with combination of the manufacturing or engineering industry and the biomedical industry. Because a lot of studies required in the biomedical things of humans. So these three solutions, what I found is initially I built this foot. So the person loses the leg, let's say above the knee or below the knee, maybe due to gangrene, maybe due to diabetes, maybe due to accident, and then the wound is sealed and the bone and the muscles are there. And then we are trying to fit the prosthetics there. Actually, the human body is not designed to transfer the load in the middle of the body, not directly to the bone. And most of the companies are trying to do that. And exoskeleton came as a separate solution, but then people thought it's only for people who have legs, not for people who do not have legs. So exoskeleton is actually the solution. The combination of prosthetics and the exoskeleton is actually the solution for future. That's what I am working now currently in my startup. We are still in a process of filing patents. So exoskeleton, which basically distributes the load slowly on the body. So starting from the amputated part, then to the little bit upper body and to the entire body. So the way load is transferred has to significantly change. That is the one thing, and that is the direction which we are working. Second thing, exoskeletons which I saw, those are very bulky. I mean, they're trying to make efforts, like especially powered exoskeleton, they're trying to make it lighter, but they're still bulky, ugly, so they need to be slim so that these people look normal, sane. So a lot of work needs to be done. We are working toward that. And this is really the advanced stage. Like I'm dreaming, if some unfortunately accident, somebody goes through accident, he's in the hospital, I think he shouldn't spend any more days, without a leg. Then and there should be a surgery, implant should be put in there, together with the exoskeleton. I think that is the direction we should be working. And there, the technology in all form, material, the mechanisms, the stress analysis, biomedical analysis, all, there is a lot of scope in this direction. Quickly, I will go through the challenges we faced in this sector. The tolerance in measurement. So whenever we are designing this for people, engineers design the technology to build the prosthetic, but how to fit it to a particular person. Somebody is tall, somebody is smaller, bigger, different weights. It's very difficult. People go get it in the one-day workshop for free. They come back and they see that it's not fitting him well. They're just using it because it's free. So tolerance, how you tolerance your designs is a very critical thing which I found. How you interact with the person, how you get the measurements accurately. Because every cut section is different in shape and size and whatever it is there. So how to deal with that? Customization is, subsequently to the tolerance. I mean, different people have different habits of walking, living, sleeping. So what they want, the customization is there, but it is not there. Or whoever is supplying customization is essentially missing. I mean, people take measurements in the workshop and they try to say it is customized, but it is not truly customized. Flexibility versus complexity. You make things more flexible, complexity grows. More complexity, cost grows. Use is, becomes preventive or prohibitive. And of course, maintenance. Somebody, comes from this leg, which is 3.5 lakhs, and the ankle is gone. Now nobody is going to pay for him for replacement of that ankle, which costs 25,000-30,000. So maintenance, repairs, these are challenges. I mean, so we need to address when we design these technologies. Customizable molds could be a technology I'm working toward. 3D printing emerging as one good solution for this domain. Plastic, composite, anything. Of course, I think we need to work on the cracks, delamination, joints, ruptures that these devices come to. Nobody thinks about it. Their job is to deliver, give it, forget it. So we need to think, because when we sell a car, having a service center, every 3 months, 6 months, 1 year, we do servicing. Servicing is an important part of the business. In fact, that's a profitable element. In this case, it is not. There is no service concept for these devices. Whereas service, it is very, very service-intensive sector. Of course, maintenance, repairs, and affordability. Without affordability, this will not survive. It will not stay another day. I mean, this number will keep growing. So affordability we need to work toward. Of course, I just want to close this thing, challenging the people here that, we talk so much on material, but also on the other side, we talk on AI. Artificial intelligence, machine learning, and also whatnot. I think disability has the maximum potential for exploiting AI technology. If it comes to blind, for example, you need to develop eyes which can directly, connect to the brain, or ears that directly go and sit and work with the cochlea, or human-powered legs, very light, ultra-light, and then walking legs, so that, we don't see disability. So AI is something. Students, if they're not there, but who is listening, I think AI, we should really try to keep disability as a target. So I will close with this. And as I said, I'm a faculty here at Ahmedabad University, and I'm a part of Composite team. So I would like to present our Composite program. So we have I'm taking Composite program. We are launching this year from 1st of October. This is a program led by Ahmedabad University jointly with ATIRA, Ahmedabad Textile Research Association, and also supported by Arvind Composites. This is a very unique program. This program completely looks at the 360-degree on composites. So talk about materials, manufacturing processes, design and analysis. I'll quickly touch on what is this program about, and I need to talk to you about it. It's really important to talk about it now because many people from industry are here, and that's the difference we are making or trying to make through this program. Yeah. I'll just let this video play. I think it's okay. So as I said, this is very unique. I mean, I've been composite student at IITM. We did some courses, but even IITs, they do not have integrated degree for composites, like masters in composites. I mean, that doesn't say that they lack expertise. I mean, they're fantastic. I mean, we are in touch with one of our advisors is Professor Bhatnagar from IIT Delhi. A lot of work has happened in IITs, in research in composites. We're just beginning, but we saw a gap that bringing all these materials, design processes, manufacturing processes, and especially the industry connect is missing from these programs. And few such programs are available worldwide. And this is probably the first one in India. This is the first program in India, actually. So we are starting it, and we are very proud of it. So this is a MTech in Composites program. So as I mentioned, it is in close connection with ATIRA and Arvind Composites as our industry partners. I will explain about the program. I'll just show you a few things. I will not take much time because this is a composite world here. They don't need to be told about it. This is our, quickly to show our team. People from industry are gathering here to help this program, help this research on composites at Ahmedabad University. We have a good team which involves people from industry. So what we have is 1 year on courses and 1 year is an internship or a thesis. 1 year courses happen at the university, 1 year internship essentially happens at the industry. So we really want to enforce that, emphasize that. 1 year which happens here at the university is heavily built upon, the curriculum is built upon hands-on. So we want to really focus on hands-on. So maximum exposure to industry practices, industry exposure we want to bring in through these courses. So hands-on is our aim. And all these courses we have built different verticals, like one vertical is on the material, one vertical is on the design, analysis and whatnot, and then one vertical is on the applications from industry, so involving the problems from industry. So like this we have built this curriculum. You can see just as a glimpse, you will, I think the brochure that is given, you can see the details on this program. I'm just not going in depth through this. So what I want to tell here is today this is a large composite community here. So we want to get composite problems from the industry, because our aim is to tie up with industry. We want to work with industry in different forms. So we would like to get typical problems that you face on material related, manufacturing related, or applications. So we would like to get those problems. We want to set a pool or database of these problems where these master students will take one of the problem and work on it. Now, how you can help us? We can send the student to your industry working on your problem as an internship. So you can sponsor a fellowship or something for that intern. That is one way we can get help from the industry, because you're gaining the insight and the knowledge and somebody is working on the problem that you face, and in return we are basically requesting for a fellowship for the student. Second thing, you give us a problem, but then we give that problem to some other industry and then it is solved, and then eventually you will get the information about that problem. Other thing is you can sponsor students for this composite program, and our aim is to make industry ready students. So to do that, we're getting a lot of industry faculties in-house here. So some people are really full-time faculties from industry. Then a lot of visiting faculties from industry are going to be part of this program. So I think what we want to deliver here is address problems from industry and create students who are industry ready. So that is the aim for this Masters in Composites program. And if we will try to communicate with you on getting input from you for this program or any relevant thing you would like to share with us. So I think that's all I want to share. So I didn't ask for questions for the previous part and this. So if you have any questions, please. Thank you. Any questions? Thank you. Thank you very much.
Thank you, Professor Gaurav, for the interesting presentation. I would like to call on stage Mr. Mukesh Sanghvi to facilitate, to honor the Professor Sham Gaurav. Yeah. So now we have Professor Hemant Chauhan from Ahmedabad University, who will talk about the journey of bulletproof jacket development. Please welcome Professor Chauhan.
Good afternoon, everyone. Thanks. This time I'm in a different role since morning. Okay, so for last more than a decade, I have been working in the domain of bulletproof jackets towards the development of actually bulletproof. So I'll take you through a small journey wherein how in the last more than 100 years, but I'll keep it short, that history part of it. So it all it began somewhere in 1500, 1600 series of the years. But in the modern world, somewhere around 1901, the first vest was actually tested. So just 125 years back, this was the way the testing was done. And this is a classic image, the second one, wherein in 1923 in Washington, a design was made to conduct a test against that time's bullet. And it was in between the two world wars that the entire bulletproofing phenomena came into existence. Early good old days, leather and silk was the only primary material. Slowly steel, metal came into picture. In the modern era, what you a majority call as aramid or the Kevlar we know. So late in 90s and till last decade, I would say, or last 15 years back, aramid was the commonly known as Kevlar was the key material. Present date, we are not dependent on any single material system. It's going to be a hybrid. We will discuss by one all of them. But primarily it is ultra high molecular weight polyethylene and ceramics. So present day, the technologies changed a lot. Okay. Before studying any issue, I call it as a virus. So if you have to develop an antivirus, first you should understand what the virus is. So in Indian context, this facility or this thing was defined as standard. So generally we follow US or the global standards, but fortunately in 2018, Indian standards were defined. So as you can see here, we have designated them as BIS level 1 to level 6. So for your ease, I have mentioned which weapon. If it is a pocket held weapon, probably it's a 9 19 mm. So you call it as a pistol. This is the smallest possible threat, and you should know that, okay, there is a speed associated with that and there is a mass of the bullet. And of course, there are some testing parameters, so you can leave that. AK-47 you keep on hearing in news and whatnot. Why so? Because it's an interesting weapon. It's short in size, it has got a good range, relatively light in weight, and it has got two locations at BIS level 2 and BIS level 5. You've got the same weapon. If I have to tell you, there are two different types of bullet, or at least for now we'll consider two. There are actually more than dozen. BIS level 2 has got 7.62 cross 39 mm. This is a mild steel core bullet. If I have to differentiate between mild steel, I have to I know there are few audience from non-engineering background. So mild steel is just like the door frame, whereas your kitchen knife is a hard steel. So it's really difficult to make a scratch on a kitchen knife, whereas you can comfortably make a scratch on any door or any general purpose steel piece. So this BIS level 2 is all about mild steel core, and we can comfortably stop it with the help of plastics and polymers. Whereas BIS level 5 used to be innovation by these three nations, that is us and our two of our closest ones. So we replace rather the core inside the bullet, which we'll see in the upcoming slide. What do we mean by that? With a harder material system. In between, we have an international standard weapon that is 7.62 cross 51 mm, also known as NATO ball. There could be variety of weapons to fire it, but it's the bullet dimension that defines that, okay, what kind of threat you are carrying, because the weight is 9.5 and your speed would be 840. This used to be all lead, but now all are using steel in that. Then INSAS, Army is not concerned, so I worked at IIT Delhi for all this matter, and INSAS was never a concern for these Army people. It was primarily AK-47 hard steel core. In Indian context, we call it as Khirki bullet, Pune. And the last one is sniper, maybe for the movies and other reasons you might have heard of. A weapon which can act as a point blank from a range of 1000 meters. A human standing 1 kilometer away is as good as a 9 mm pistol touching your skin. That is the power of a sniper, which we'll see in the upcoming slide why so. And there goes the higher speeds as well. So I presume we all are very much on the same page as far as virus is concerned. This is derived primarily from the US standard. So in the US standard, that is NIJ, level 2A, level 2, and till the end of 3A, that is 0.44 magnum, all bullets can be stopped by a soft armor barrel. They are easy to stop, relatively easy, or we call them as these are pocket held weapons. After that, they directly have an international standard, NATO standard bullet, that is 7.62 cross 51 mm or M80 NATO ball, and then US has got APM2. They call it simply M2, that is their US standard sniper. India generally followed Russia for that matter, so we follow Russian Dragunov. So we have a slightly different this version, we call it 54R API, that is armor piercing incendiary. Now to understand what do we mean by that, because we are not going to stop one bullet. So what is the kinetic energy of one? So over here, if I look at this, it is just below 700 joules of kinetic energy. If I go to this AK-47, it is above 2000. If we go for the international standard, it is above 3000. But this is really dangerous. It has got the hardest possible, which we'll see in the upcoming slide. The bullet is the most lethal one. And in reality, the energy approaches 4000 joules. 150 joule is more than sufficient to kill a human. Impact, a head injury is more than sufficient to kill a human. We are talking somewhere close to 4000. So that is the power of the so-called bullet. Now what is inside this bullet? So we used to machine them, we are engineers, so we cut them. We want to know what is inside this virus. So we learned that, okay, mild steel has got a relatively flatter shape surrounded by some blackish material that happens to be lead. And of course, to increase the life of the barrel, steel barrel, we always provide a brass or a copper jacketing. That is what we call as the FMJ, full metal jacketed. That is basically a covering of brass, so that my barrel is not worn. If both the steel is there, that is the barrel as well as the bullet is steel, then my barrel won't last very long. If we cut the complete bullet, we found that, okay, there are variety of cores inside. So if we look at only the left side of it, this tip is very sharp compared to the other one, which is this bottommost mild steel is an international standard AK-47 bullet, which is a mild steel core bullet. Whereas this one, it's available only with India and two of the northern region neighbors. If we look at the hardness, typically the hardness of mild steel, MSC is 20 to 25, whereas for HSC it is 50 plus minus 5. So unfortunately, no plastic can handle this kind of tool or this kind of hardness at that given energies. And if we look at the sniper, it is even harder. To give a scientific challenge, in India, we do not produce the core. This particular pin you can see, this is what we call as the steel core of a projectile or the bullet. We are still date not producing this 65 plus minus HRC core. We import it and then we convert it into a bullet, or we directly import the bullet completely. So that way the shape, the size, the material is the most important, and not that outside yellow colored material, the brass. It is the inside that counts, and the hardness is the key, because we can comfortably stop the brass and the lead. But when it comes to the hardness of the steel, that becomes a real challenge. And if I know what you are wearing, the other person is wearing, you just need to increase this powdered part, which happens to be the explosive. So let's say you are having a Indian AK-47 HSC. So the speed is 710 meters per second. If you increase the weight of the explosive by few milligrams, your bullet will be moving at a speed of say 750, and you designed a jacket for 715 or 710 plus minus 15. So that is where the things matter. So we are looking for two types of panels. One is soft armor panel, which is close to the human body, or touching the human body, in general it is termed as the vest. So if someone is wearing it, you won't be able to differentiate that if he is wearing it or not. Whereas a hard armor panel, which is the front side in this figure, it has got so many components. The two primary things are, first we need to erode the steel part. Second, we need to stop the debris of the steel as well as whatever we have broken in the name of stopping this projectile. So we have boron or silicon or aluminum oxide as in ceramics. It could be single material or hybrid. That is the front part of it. Basically, we look to either break the bullet, grind the bullet, blunt the bullet. Those are the only ways that we can limit it. In the process, we will end up damaging this ceramic. If I am having a cup of tea and I drop it, that too is a ceramic. So ceramics are extremely brittle or very poor in tension. So they can't take bending loads, they can't take tensile loads, so that will break. So there will be a lot of crushing. Now we need to trap that entire crushed ceramic along with the debris of maybe two or more than two pieces of grinded bullet. Those needs to be stopped. So we need a backing, and over there we solely rely on fiber reinforced composites. Earlier this used to be Kevlar, now we don't prefer that. Companies are using it for, of course, the commercial cost reasons, but UHMWP happens to be the best serving material. In engineering, if you are doing something, design is a must. So finite element based simulations or designs are the first step to start with, but unfortunately, I said unfortunately because in balastics we don't know the answer. Fortunately, in all other engineering domains, we are not designing the product to damage it. We design the product such that it remains within the yield limit. We always look for that the loading will be well within the modulus of elasticity of a material system, and in case of bullet, we are very much sure that the very loading point would result in damage, that is crossing the ultimate tensile or ultimate compression, the ultimate strength point basically. So the challenges are multifold. Still, you need to characterize what materials you are having, determine all possible properties with respect to a balastics model, and then let's see how your things are working. So at the top we have got a ceramic layer, and at the back we are planning for some UHMW, define all the properties. Yet it might not do like that, because when I fire single bullet, the bullet is stopped and I can see so many cracks. So can I fire a second bullet? Because there are many unanswered questions. In reality, a panel will be tested against either 6 bullets or 8 bullets. So if it's a sniper, it's a 6 bullet, 9 mm will be a 6 bullet, in between all will be tested against 8 bullets, which is quite a large number, and it is assumed or it is expected that a human is wearing a 1000 centimeter panel, that is the human chest area, and 8 bullets are to be fired within this smaller space. And needless to tell, 1 bullet is more than sufficient to kill a human. So there are many unanswered, and how these cracks will propagate, what kind of damages will happen. So designing becomes challenging. And as Professor Shyam mentioned, he is going to teach these aspects of design in the course of Masters of Composite. So here we see what happens. The important thing is how time plays a critical role. 100 into 10 to the power minus 6 was the time the bullet is completely either stopped or perforated. So either the life is saved or killed. So we simulate that what happens when the bullet velocity increases, and at what point of time or at what speed of this projectile there will be a perforation. That can be converted into the kinetic energy profiles. So we designed a system at least 735, 710 plus minus 15, so that brings us to 725 kind of. So you can precisely calculate and design. But again, something unique with the composites is that it's not a metal. Had it been metal, we could have casted it and rolled it. Things would have been uniform, but here every specimen is to be made precisely. So that way things are challenging, and we could precisely calculate that, okay, what should be the thickness of the given material. Moving on, what material? So we already mentioned that, okay, material is important. Everyone is moving from metals or homogeneous materials to composites for the directional properties. Now, this particular slide gives, or this particular image, I would say, since it was created by Honeywell, so that's why it says Spectra. Spectra is basically the commercial name of the ultra high molecular weight fiber grade developed by Honeywell, USA. So we see steel is somewhere at the bottom. Okay, modulus and tenacity are two things which are always not in proportion. So you try to increase one, someone will go down. Whereas in belastics, steel we can't change. What it is, it will remain the same. Glass, there is a positioning and you can't expect much. What we are expecting that the tenacity, the definition if someone is not clear about, and modulus, both should be as high as possible. So that is where the entire game changed. That Kevlar, when came into existence, it was very good material, but now we have reached the limiting condition of the polymer chemistry of Kevlars. So it's not, it can't move ahead much. Whereas UHMP started close to Kevlars and now it is moving up. Both the modulus and tenacity, that is the diameter is decreasing, density is decreasing, and strength is increasing. So that is the beauty of UHMWP. Kevlar is the second best material, but there are few issues with that, yet it is required. For few specific reasons, Kevlar is required. So what specific attribute? This high strength, excellent chemical resistance. By the way, let me tell you, UHMWP is that simple plastic bag which you carry for the household stuff. It's only the ultra high molecular weight of this polymer change that matters. Otherwise, it's just a polyethylene, the bag of polyethylene. The density of a UHMWP made composite panel is 0.97. Water is 1. So that way, it also serves the purpose of floating a human body. It helps in actually crossing the river, or it won't let you drown in a accidental case. And plastics are not happy with water, so they are hydrophobic in nature. They repel it, whereas Kevlar absorbs, or the properties of Kevlar deteriorate when exposed to UV or sunlight and moisture. Whereas UHMWP is not at all affected by moisture, though light might affect, but not much study is available. The biggest benefit associated with UHMWP is its ballistic resistance, that is the bulletproofing capabilities, other than the other properties. Now, what should be, in what form we should use? So the most common one known to us are like 2D woven. So we'll have two fibers, one moving along x-axis, another along y-axis, and they are intertwined with each other the way this image shows. So there is a warp and a weft fiber. But the issue with the system is one of the fiber, if kept straight, the other one will have to move like a wave. So in that case, you are not exploiting the best possible properties of that material. So that is the reason that in case of UHMWP, we look for UD ply, that is unidirectional plies. So this figure shows most of the commercial grades of UHMWP, they have 4 plies of 090, 090, and that makes one thin layer of fabric. And if we cut a ply and see a scanning electron microscopy, then this is how they look like. So the long pipe type of things, they are the longitudinal fiber, and all the circles are the 90 degree, that is a perpendicular fiber. This is how the fabric looks like, and this is of course a tested laminate. Still, what is the biggest challenge? As we know, it's a plastic. So melting point is, of course, it is somewhere around 142, 144 for polyethylene. So beyond that temperature, things are in trouble, and hardness of bullet, which is beyond our control because it will be fired. So the moment we say that we are exceeding the limits of 25 HRC or mild steel core bullet, plastics can't handle that much of. We can increase the thickness, we can restrict or limit the kinetic energy had it been a lead or a mild steel. But since it's a hard steel bullet, AK or a sniper, these materials are not going to serve. Yet we need to stop the bullet. So we studied variety of materials, means the mankind. Steel is the best possible option, but the density is the biggest challenge, 8,000 almost. So the best outcome came in the form of ceramics. ceramics have some unique properties that they have very good compressive strength, they have the ability to wear any material. The only challenge associated with ceramics is they are very poor in bending and tension. So if there is any kind of bending phenomena, the strain to failure is very, very low. So the moment we will try to press the bullet inside, it will develop a brittle failure or brittle crack in the material. The most commonly used materials for this case are boron carbide, silicon carbide, and to some extent aluminum oxide as well. Presently, the cost efficient solutions are comprising of a hybrid of boron and silicon, because boron is very costly and silicon is slightly less, but the density of silicon is slightly higher than boron. So it's like a compromise between the cost and the technology. If you want to go for the best possible solution, go with boron carbide, but then the costs are highest possible. And many of the studies were done to see how the penetration happens in this case. So the projectile damages ceramic at its leading surface. So in this figure, these are the few of the earlier ones, that how the material gets lifted, how a cavity is created, the fragmentation will be done, and there will be zone wherein the material will try to bend and cracks will initiate. But we need to stop that. I mean, this is unavoidable. So in the next figure, we'll come to know what exactly is the mechanism. The moment the bullet hits, there will be a zone of compression. So there is a projectile. When it touches the ceramic, it will try to create a zone of compression. As a result of this compression, a stress wave will travel through the depth direction, along the depth direction till the end of the specimen, and that will lead to shearing, compression of the material ahead of it. So that will result into pulverization, converting the ceramic back into powder or pieces at least. In turn, that will lead to compression, and that means tensile phenomena. We are trying to bend a specimen, and we already discussed that ceramics are very poor in tension. If I have that teacup, I can't bend it. Had it been a plastic, I can comfortably bend it. So as a result, there will be a lot of damage. Now, the good part is my tip of the bullet is damaged because of this abrasive tool. Lot of material of high hardness, that steel, is quite worn, that is grinding phenomena is done, but now we have got lot of debris of this ceramic along with two or more than two pieces of left out bullets, which are still moving at a very high kinetic energy. So at the back of that, will place a backing material, and that backing material can be ultra high molecular weight polyethylene. And this is how either a crack will grow like this. So here we can see that, okay, there is a bending phenomena. Part of material is trying to remain there and a part is being pushed. So a specific type of cone will be created depending on the composition and the processing, what we have done with the ceramics. And in turn, this tip of the bullet will perform the phenomena of grinding or pulverization of the material in front of it. These are few of the very critical studies wherein it was studied with the fast flashing X-rays that how the crack propagates. So we observed the radially outward moving as well as the circumferential, circular kind of cracks. When a bullet hits, this entire ceramic is one piece. So we can see the crack extending till the edges. And that very figure confirms that second and third bullet is not a very good idea. Because if unfortunately, if I say that at this point next to D, my red marker is the spot of bullet, so we can comfortably appreciate this fact that it has got a good space to move in between a cracked line. So perforation is possible. If not second, maybe third, maybe fourth, we have to go till 7 and 8. In another study, it was studied with in the perpendicular direction what happens. So it was primarily to study how much material of ceramic is lost and what kind of damage and deformation with respect to time the projectile is going through. APM2 moves at 860, 870 meters. So the time requirements are going down. Within a very short span of time, the entire phenomena is over. So now let's come to the manufacturing. I won't touch deep into, I knew that many of the presenters before me have discussed this. So this is a unique system which was primarily developed for automobile industry, but in the processing of polymer based composites, compression molding is the key process for processing of UHMWPs or even Kevlars. So this is one of the cycle which we use to make. The difference is that the pressure required here are very, very high. And why I mentioned pressure, for temperature processing of any material, the temperature might be defined by the OEM, the supplier of the raw material. In a study, what we did, we performed the compression molding at a pressure of 34.5 bar or constant, means kept the grade constant, and for the very obvious reasons I can't declare the grades here. So we found that the strength of this material is somewhere around 450 megapascal. Then we increased, the temperature remains constant, the processing time was 30 minutes. We increased the pressure by 4 times. So basically I am having, let's say, 10 layers of a material. Earlier that was pressed at 34.5. And in the another specimen or another cycle, it was pressed at 4 times the pressure, that is 138 megapascal. And we observed that the strength has increased from almost 450 to nearly 600 megapascal. Now this is the beauty that many starts the business of ballastics and bulletproofing. They say that we know how many layers are required and we'll make it. But we miss to optimize the processing parameters, and there is a very thin line or there is a very small zone of optimal processing area, what we call as. So that is how these things matter. And when you make a product at a less optimized parameters, then to study that, we conduct non-destructive testing. So this is the image of a ultrasonic C scan. Those who are from the subject, they know, yesterday we had a full lecture on this NDTs. So ultrasonic C scan has got both, 3 of them, A scan, B scan and C scan. And in C scan, we can see this should have been completely, this part is the neck protection, the HAP part of human body neck to be protected. The shape, blue color is pretty clear that, okay, where is my hand is the location, but I can see a lot of whites here. It means lack of pressure or incomplete consolidation of the material. Had it been the perfect one, all reds and whites, reds means defect and whites mean inappropriate consolidation. If it is a perfectly consolidated material, then the outcome of a C scan would be a completely blue screen, something like this. Though it has got couple of defects, but they might not be visible. Okay, over here I can see something just above my cursor. So these type of very fine defects are acceptable, but not the previous screen. Now how to integrate ceramics with UHMWPs. So in one of the image we have seen that if the ceramic plate is integral, that is one piece, or we call it as the monolithic ceramic, then one bullet is sufficient to generate cracks till the end. So what we did, we took 30 mm hacks or 30 mm square tiles, so that when a bullet hits, only a small group of maybe 1 or maximum 7 tiles, that is 1 at the center and 6 touching it, will be damaged. Other sides are at least safe. And the process required here is, you should first have your compression molded UHMWP laminate ready, and then there is an entire series what we call as the process of autoclave. So many of the presenters before me have discussed, I won't go into that. We need to apply a suitable glue on top of UHMWP, appropriately treated ceramic, wrap it with, this yellow color is all about Kevlar. Now this also is a unique phenomena. You need one layer of Kevlar. When we are spending so much on UHMWPs, we could have skipped Kevlar for one layer, but the properties we are getting and the the resulting outcomes, they are well met by Kevlar, not by UHMWP. So there we have to study and optimize our system, and this is a cycle which we follow for autoclave. So with that, we come to a point wherein we got a BIS level 2 and level 3 panel. BIS level 2 and 3 means MSC AK-47 and this M80 NATO ball. Whereas level 5 and 6 is AK-47 hard steel and a sniper. So this is how the panels look like. If you are interested, you can contact me later. I have it. testing. If you have a panel, go for the testing. So it feels like that, okay, we should have a weapon, fire it and over. It's not over. There is a BIS standard and there is a test protocol, and that is really very, very rigorous. Why so? Because we made a panel today and we will test it tomorrow. Definitely the bullet will stop. But maybe the panel will be used 5 years from now, or it was being used but there was no bullet hit, luckily. What is the condition of the panel 5 years from now? So for that we have an aging cycle. There is a 11-day thermomechanical conditioning cycle, wherein in the span of a very short 11-day cycle, it is equal to 5-year lived ballistic panel, and then testing is to be done. So generally a fresh made panel on 12th day may fail. Likewise, an army man may have to cross a river body, or there could be shower at any moment of time, of like we are crossing every now and then. So if wetted, because in case of steel there was no issue, then came Kevlar. For almost 30 years Kevlar was the boss, market leader, and it was very well affected by moisture. So there was a scheme for, in internationals it is 1 hour 60 minutes, and in Indian standard it is now 30 minutes, because of the obvious reason that now we have technologies to seal the panel perfectly. So there is no scope of water ingress. None of the test agency allows you to take a picture, but for your understanding, I took pictures from some of the army base and they are unnamed, so it's fine. The standard is 10-meter distance, so there will be a tip of the barrel from which the bullet will exit, and exactly at 10-meter distance should be your target. Over there, we place a chronograph. In reality, we have IR screens, but in a field trial, we can't have the IR screens. It's a complex phenomena. So we placed a mechanism basically to measure the speed of the bullet just before it hits the panel, that is 2.5 meters from the panel to be tested. And to record how the entire event happened, we used to have a high-speed camera. So in this particular setup, this weapon is 6-AUR. This is a US weapon. At a distance of 10 meter from the panel, over there we have this ballistic chronograph as well. On the sides we placed a Motion Pro 7 high-speed camera basically. I'll share one of the result of this high-speed testing as well. But for now, let's continue with, if we tested n number of panels, can we have some sciences behind? So we developed a unique scheme for AK-47 at least, that on one side of, I hope you can appreciate that on one side of this central original core, that is unimpacted bullets, we cut the bullet and took out the steel part of it. On left side, I hope all of you can appreciate the heights are less compared to the right side. We analyzed if bullet is stopped, the amount of wear, reduction in length and reduction in weight can be very well correlated with a safe zone. So now we know that if the length of AK-47 core, residual core, is more than X, most probably it is perforated. Proportionally, there will be a weight as well. So we correlated that and we've established a relation. So it is this small 5.2 grams of steel which matters the most. If you have done everything, now let's better fine tune our simulation model, because we discussed at the very beginning that we don't have the properties, and whatever we use, generally we prefer that, okay, within the yield limit. But here everything will damage. So we optimize our model and we correlate that, okay, if I have a single shot phenomena, how does it goes? So we match them. And if things are moving fine, that's good. Good for us, or we can further optimize that. How about the mild steel core? So this is how a mild steel, that is a deformable steel, will look like when trapped inside the panel. So couple of slides back I've shown you a white colored panel. It is that panel only after hitting 8 shots of MSC, that is mild steel core AK-47. The bullets are trapped inside. They are very well deformed. Now the beauty is that with the first shot, the depth of penetration will be minimum. But as you move on, it will keep on increasing in terms of depth. Okay. Can we have NDT of the panel as well? Because ultrasonic C scan of UHMWP is possible. But for the small pieces of tiles, it is impossible to go for ultrasonic C scan. So we used to go for CT scan. I hope majority of us knows what is CT scan. Known to you is for medical applications for human body. We used to use the machine for our ballistic panel before the test and after the test. So here you are observing those final panels where we cleared all the test protocols. 6 shots of sniper are fired and we can see that first bullet is somewhere over here, whereas the 6th bullet has gone much farther. Or the panel, okay, look at this particular curvature. It is pretty consistent. The extraordinary white top part is ceramic and less white part where my cursor is right now is the UHMWB part of it. And as the bullet hits the first and second bullet, there was a localized deformation. And as we move on, 6th bullet, the entire panel at the back has gone curved. And on the front face, now we observe that, okay, for this one I can see maximum damage. So maybe 4 or 5 tiles are damaged over here. But rest of the panel is still integral. Similarly, for this was for sniper, this is for AK-47. The issue with this kind of a system is human body is not flat. There is a curvature. So when we place the small tiles on curvature, there is a possibility of defective zone. I hope you can appreciate the gap over here. But fortunately, it is at the edge. So we have a lot of rules to follow when testing. So from any of the edge and in between any 2 shots, we cannot fire within a distance of 51 mm. Or simply put, no 2 shots can be closer than 51 mm. So from this edge also you have to be away by 51 and the tile is 30 mm. So this point is safe, but there was a defect visible over here as well. Defect in the sense that there is a minor gap between the 2 tiles. If bullet hits exactly at this point, there is a fairly good possibility that bullet will make out a way in between the 2 tiles. So the test agency will take an X-ray of this, will mark the exact spot where maximum gap is there and they will fire the bullet there. And that is what they call as the testing is always done under the most rigorous condition because it's the question of life and death of a soldier. So we tested all of them. These are all post TMC, that is after thermomechanical conditioning. Or put it in a simple way, it is a panel which was made last month, but it has lived a life of 5 years. So after 5 years also all 8 bullets are stopped. The level 2 and 3, as I mentioned earlier, lead and mild steel, they are very easy to stop. So this is what we did in 2021. Back face signature is another important phenomena. We have seen deformation in these CT scans. So this deformation is to be taken up by the human body, and that's why we have a soft armor panel, something which I didn't discuss because that's a very easy job. Stopping a 9 mm bullet is like when you are dealing with sniper and AKs, stopping a pistol, which is a pocket held weapon, is very, very easy. Though it has got 600 plus joules of energy, so one bullet has got sufficient energy to kill more than one. Fire. So these were 4 shots fired. We all heard of what happened in Mumbai long back. So in case of automatics, this was a 6 or sniper, M80 ball. Yeah, M80 ball. The challenge is there will be a minor vibration because you are human. So when one bullet comes out, there will be a shake in the barrel and there will be an impact on the shoulder. A cartridge could be of 20 bullets or more than that. If 20 bullets are moving as if droplets of rain, he cannot aim at one point. So what we did, the standard is 3 bullets. If you have to go for a burst fire, it has to be a burst of 3 bullets. But no trained army men having a highest experience of 23 years, he couldn't make it happen that 3 shots are fired and all 3 of them are on this single panel. So what we did, we divided this experiment into two parts. You can see here probably there is a left guy over here, left barrel, and there is a right barrel. So on the sound of fire, 2 bullets from left and 2 bullets from right, so that in total at least 3 bullets hits. And we recorded this phenomena at a speed of 10,000 frames per second. Other way around, how many rounds this weapon can fire. So when we say that, okay, this particular rifle can fire n100 or few hundred or whatever thousand number of bullet, this is what we mean. That you give a belt, either a bullet belt or a cartridge of 30-36. So within less than a minute time, your cartridge is empty. But there is a human in front of it. So this was the condition of the panel. So 2 bullets from left side and 2 from right, and all 4 are stopped at the back. What will happen with the human body? Now this sounds, it feels with the pictures and results that everything is good. Yet if we look at another panel wherein few of the conditions couldn't be met, because the standards will always say that, okay, this is the set of conditions to be followed or to be met. What if the bullet hits at a 25 mm? We said that it should be 51 mm away from edges and no 2 bullets close to 51 mm. But bullet won't follow, it won't hear. So if it touches the corner of a panel, something like this, it will lead to this kind of a deformation. Now this is a image from internet, of course. So this is what a 750 centimeter square panel looks like, the grey part of it. In Indian Army, the requirement is 1000 centimeters, so it is slightly bigger than this. Yet, if this kind of back face deformation is going to happen, it is more than sufficient to comfortably break the rib cage that will lead to immediate entrance of blood into the lungs or bursting of heart or liver. If that happens, that soldier was lucky guy because he died immediately. If there is a lung puncture, he will definitely die, but slowly. If he couldn't be taken to the hospital, and generally in their case what happens is that these jackets, I can't cover all the aspects of it, the jackets have a quick release mechanism. So within 3 seconds time, if someone is hit at the center, his partner or the co-army man, he will pull a string, the jacket is open. So his chest is open basically, visible. Within 3 seconds he can see, oh, you have got no blood. So you are good. But he can't stand because he has just now encountered 2000 or 3000 joules of energy. So that was a huge punch. So he will say that, okay, you be side of this wall, we have got an operation of 6 hours. We'll go 4 hours up and 2 hours down. And while coming back, we will pick you. And while coming back, most probably they will find a dead body. Even if he is alive, so much of blood has gone in and we don't know where is the base, how much distant it is. So the chances are. So there is a lot to be done yet. As far as rules are concerned, we follow the rules and we clear the test protocol. So jackets are to be designed like that. Somewhere we'll have to make a hard stop that, okay, we can't go beyond that. Like the discussions at the PAS or the International Personal Armor Committee level is that what should be the minimum distance between the 2 shots? What if the rain, that is that n number of this 100 bullets and 150 bullets per minute, if they are coming at a single spot or very close by, so there is a fight between the two that, okay, 51 mm or 25 mm. Because 25 is too close. We have seen the damage zone, which was pretty large. This is a simple one for your understanding. This is a video. Okay. This is a 9 mm bullet, pistol, which you normally see with any policeman. So this is a flexible material UHMWP which can comfortably stop the bullet. You can see the bullet as well. And there comes a second one. Now see the type of deformation it is going through. Though the bullet is stopped, the right side of the image we can see the back of this panel which is intact. There is no hole. So both the bullets are comfortably stopped. But if we look at this particular phenomena, how the fabric has bent, the time between these two shots is 0.05 seconds. The second bullet is coming much faster. And in case of rifles, it is somewhere around 0.02 seconds. The nth or the second bullet is coming. So what all we are looking for? We are looking for ballistic performance. The first target is please stop the bullet. Even if stopped, what is the blunt trauma? The deformation inside the human body is the blunt trauma. If it is beyond a limit in NIJ, that is US standard, it is allowed to go till 44 mm. They say that the US soldier has got a good healthy adipose tissue. So there the chest muscle, simply put, or the muscles are quite thick. But in Indian context, they are much thinner. So the limit is 25 mm. And 25 mm, though sounds good number, but it's very small when it comes to stopping the bullet. And in one of the slides, I have shown that for mild steel and NATO ball, we could stop the bullet within 10 mm of, or for NATO ball, actually it is 13 point something. But it is half of what the standards allow, 25 mm. Then how about the multi-hit? It's not just one bullet. We are going to fire maybe 6 or 8 bullets. We need a setup very close to the bullet itself. These setups are very, very costly affairs. And we need to measure both the entry velocity and if there is an exit, what was the exit velocity? There lies the rare of the rarest phenomena that bullet perforated, it passed the panel, but velocity was such that skin could or the clothes could stop the bullet. So still the life is saved. Then how about the comfort and ergonomics? So with the numbers of what we have, the jacket, basically it's all about the ergonomics of the drawing and the weight that matters. And we have been working on reduction of the weight. So I'll come to that in a couple of slides later. And then finally the environmental resistance. Kashmir is Kashmir, Rajasthan is Rajasthan, I can't help it, nor can you. There is a temperature, there is a weather, there is a moisture. So a lot of environmental parameters, they may also hamper the performance of a composite system. Even if someone is making it, then there is a second level of challenge, meeting all the compliances, certifications, agencies. So to get the certificate, unfortunately in Indian context, we don't have a certification scheme. NIJ, US and the West world, they have the certification. You once take the certificate and start producing till we upgrade the standard or we change the standard. So achieving this certification to be recognized as a ballistic standard is essential for manufacturer and supplier, first issue. Then adherence to these protocols is another level. If you are making these panels, you have to have quality assurance. So putting the long story short, when this army order is supplied, one truck will carry 5,000 jackets. 10 jackets will be picked randomly, and if any kind of failure is occurred, not about the only stopping the bullet, one of the back face signature turned out to be 25.1. It's just 0.1 mm. And we know from the recent news what is the impact of 100 grams from sports. So 0.1 mm of exceeding the limit is equal to 5,000 jackets rejected. And it's a huge cost associated with that. And then know the right market. Even if you have certificate, you know all the quality standards, accessing the right market with the right certification is another level of challenge. So there is a strong need for specialized labs, dedicated specialized ballistic testing laboratories. In India, we have only two. One for defense, that is in Chandigarh, and fortunately one for Home Ministry is very close to you, is in Gandhinagar. Then we require highly trained, skilled staff. And that is where we are planning, we chip in that at research level, at PhD level and onwards, we have lot of composite stories. But when it comes to ground, who will operate the autoclave? Who will operate the compression molding machine? Who will perform all the cutting, manufacturing operations? For that we require labor. the manpower on the floor, and that needs to be trained, and none of the PhDs will generally go to that level. So we need to disseminate that information, that knowledge to the next level. That happens to be the MTech. So we are in that phase that, okay, let's start with masters, then bachelors will know, and then only the things will percolate down to the shop floor so that we can produce the best quality composites, something which India is lacking till date. And that can be comfortably proven by the growth of the aerospace industries, which happened 2 to 3 decades back in the West world, which is pacing now in India. And accreditation. So I think we are very well known to them. At IIT Delhi, what we could achieve was that when we started in 2017, the Indian standard was a 10.4 kilogram jacket that was compliant to as per NIJ, because in 2017 there was no BIS. So we had a set of rules, a question paper you can say, that AK-47 hard steel core is the largest threat we have, and you need to decrease the weight of this 10.4 to somewhere around 8 kilogram. We were on that path, and 2018 came and BIS standard came. So there was a minor variation in the speeds of the bullet and types of bullet and whatnot. So actually the question paper changed in between when I was answering. And by the end of the project, that is somewhere in between COVID times, Indian Army said, we have no threat because of AK-47 now at the Kashmir part of it. So we are only interested in sniper now. Your front of the jacket should have protection against sniper. So again, the question paper changed towards the end of the project. So, and unfortunately for that part, there was no standard jacket available in India. So we could come up with, for both the solutions, we brought down the weight of a 10.4 plus kg jacket of 2017 Indian standard to 8.2 kilogram. It is 8 plus minus 200 grams it runs. So it is generally 8 to 8.2 kilograms. When we have a front of, as in this case we can see, it has got a front to protect the 1000 centimeter area of front. It is this part which has got AK-47 or sniper hard steel. A back, both the sides, that is both the kidneys you can say, the groin area and the throat. The throat has got full 360-degree protection against 9mm pistol, but only rifle protection is given to the front part of it. So this is what we could achieve, and this took us a bit of time. And this was done at IIT Delhi. Now at Ahmedabad University, we are coming up with all the facilities. You have seen the images of the cut section of the panel after bullet impact. So that requires a very precise machining process. So let me share some experience. We touched a tool, the fiber was pulled out. We tried laser. It was found to be solid state laser transparent. We tried with CO2, 150 degree was melting point, so we ended actually burning a lot of material. So finally we could optimize with water jet. Water is the best material to cut this panel, and water is the best material to cut the food as well. So we are going to have that facility as well here. We are going to, at this campus, we are going to have water jet and compression molding for MTech composites. And for autoclave, we are having a tie-up with Atira. They are having this, they are in the process of getting this large commercial autoclave, because they are primarily into the parts for ISRO. So what and where is the future? Yes, we are looking for increased protection. What should be the ideal weight for a bulletproof jacket? Or what can be the ideal material for bulletproof, if I may? Air is the best possible bulletproof jacket. The solution is, if there is a rifle, it has got a range of 500 meters, you stand at 800 meters, air has got sufficient resistance and earth has got sufficient gravity, the bullet will fall. But army mind can't say that. So we could pull it from 10 plus to 8, and the army says that why can't you make it half kg or 0 kg kind of. So there lies a lot of scope in that domain. Then enhanced comfort. If you are given with a 1 inch or a 20 mm thick plate in front of your body and something on the side and back and neck, You just can't move your head like that with all the safety gears in place. So comfort is another important thing that is only possible when you decrease the thickness and decrease the weight. So there again lies a lot of scope, and then integration of technologies. That is something which everyone is talking, but not much is going on that front. So a lot of scope lies on front of getting the real-time data. What kind of health he is having. Like a CEO sitting at the base, he says that you have crossed that peak and now you start firing. He says that, sir, I have climbed 200 meters and now I am dying for the breath. So the comfort has got a role. So why can't we have the integrated medical technologies that CEO knows that out of these 8 men, how many are in what condition, or all of them for that matter. Accordingly, he can plan the strategies better. Likewise, after the shot, what is the condition? And why to have a shot? Why not to have more gadgets inbuilt into that? So that is what I expect that in future, that is here at Ahmedabad, I am going to have a bulletproofing facility. We are in progress of that in composites, we will start more studies on the composite materials, then incorporating nanotechnology. Like in the morning session, Bitra director, he mentioned that not just the carbon fiber, they have incorporated 0.05% of CNTs into the fiber that will enhance the properties like anything. So if we can incorporate that at the commercial level, the weights will come down drastically. Biomimicry, what commonly known is that self-healing or self-repairing kind of phenomena. So on those directions also, or at least repairing the BPJs, because the BPJ plates cost a lot. So if one bullet is hit, we say one life is saved. That is one part of it. But then a huge cost is gone. Apart from that, the development of more and more lighter, more and more flexible and self-healing coatings, so that the material can take care of itself, and with lot of integrated sensors if we can have, nothing like that. So on that front, I would like to take few moments extra. We at School of Engineering are very soon going to have a learning factory wherein a fully automated factory floor will be coming into existence, and KUKA robots, they are supplying us metal printers, not just the 3D printing by polymers, but metal printers will be coming up. Basically, it will be a place, it is going to very soon, a place wherein the staffs can be trained or will be trained to work in a fully automated factory, which could be a manless, only programming is to be done outside, then how the entire factory scenario, the modern world works like. So we are working on those lines to have a world-class facility here. In terms of bulletproof, coming back, in technology world, we have a term called as TRL level. So generally, or even in last 1.5 days, you must have seen many of the technological outcome, that is the outcome of research is presented. That lies somewhere around basic principle and a concept and a proof of concept at the max. So we say that, okay, the TRL level is 1, 2, 3, 4, that's it. The education institutions generally don't go beyond that, but we at IIT could deliver. It took a bit of time, but now we have all the relevant experience. So we have integrated pilot system demonstrated. The product has complied and met all the standard requirements, and now it is going to the private players for mass production. And that thing is a closed chapter. Now we are going to further continue on that journey, that why can't this 8 kilogram be bring down to 7 kilogram and 9+ kilogram to whatever less we can. Of course, academics will never go for mass production. That is the responsibility of the private limited companies for that matter. So from that point onwards, we will hand it over to the industries, and for that, we wish to collaborate with the industry partners, as my colleague Professor Shyam mentioned, that you promote your staffs or sponsor your staff so that they can be here for 2 semesters, study the composite, and then take up your projects. Not necessarily bulletproof. It cannot be everyone's field of interest, but it could be your area of interest. So this is what we could do, and this is one of the recent ones wherein at IIT Hyderabad, I presented it to one of the minister. What is his name? Dharmendra Pradhan. Is there a mistake? No, I'm asking you to think. So you please think what directions we wish to move. Shall we be static? No, definitely not. All those who are in this hall, they are definitely desperate and sincere towards the growth of composites and towards the growth of their own career and industry. So this is the right time that whatever area we are into composites or integration of technologies, as Professor Shyam also mentioned that he is using the technology. So when he says EV, it has got both. Composite is there and there is automation. So is the Dean mentioning that, okay, we are going to have a factory of future. That is the learning factory with all automation in that. So I welcome you all once again. And if you have any questions related to bulletproofing or any other subjects, I'll be more than happy to help you out. Thank you. Sorry, third one is boron carbide. Okay, yeah. But that is not, that was just the initial trend some 12-15 years back when it started. It turned out to be a very good material. I got your point taken. I mean, I hope if it is not answered, then do let me remove. UHNP was growing, so was PBOs, but PBO turned out to be because of the environmental factors, it degrades very fast. So that was the challenge with that. So it was, it came very fast and it fall down very fast. Anything else?
You have mentioned that when bullet hits to the ceramic panel, so it will crack suddenly from that point of.
Yeah, radial and circumferential.
So have you done any damage mechanics or fracture mechanics study when back propagates and how it will damage the system?
We did try it, and we have a camera which has got a speed of 10 lakh frames per second, and we found that 10 lakh is too small a number. Oh, sorry, 1 lakh. 1 lakh frames per second is a small number. We require more than 3 lakhs frames per second to track or to measure the speed of growth of crack in a piece of glass. I request those who are students, if here anyone, and if you happen to find a piece of glass somewhere in the scrap piece, place it away, try to strike it, record it, and let's try to see what is the speed of propagation of crack, how fast the glass breaks basically. So we attempted and we found that we require even higher speed cameras. It is going in lakhs, but we can't measure that. I mean, with the facilities we have, we couldn't. But we did store that, okay, first this crack goes out and then circles up. So circumferential and radial thing is clear, but speeds are to be measured. Anyone else? Yeah, please.
Can we use polyurea? Polyurea resin.
Any and every material is good for bulletproofing. You'll have to only increase the thickness. In here I said that much of thickness. In UHMWP, the beauty is, like if I have to share a number, 1.2 kilogram and 13 mm thick is the requirement for UHMWP for a specific grade, 13 millimeter. It's more than sufficient. If I go for Kevlar, this will be about 20 millimeter, well above 20 millimeter. And now if I keep on decreasing, I have shown one of the figure wherein I have mentioned the modulus and tenacity both are rising. So if I go for steel, I'll have to come down. That means the weights will increase or the thickness will increase.
Because polyurea has excellent blast proof properties.
Yeah, that is right. There we are playing with the blast wave. So you need to stop the shock wave and the blast wave. The wave is being stopped by the foam part of it. But how about the sharpness or the projectiles? For that we require this kind of material only. Thank you.
Thank you, Professor Chauhan, for the fantastic learning. Now I'll request Professor Dr. Sharma,
So we'll take a short tea break at the exhibition hall. We'll be back at 4:15.
Hello? Good
Yes.
afternoon. Can you hear me?
Yes, sir. Just a minute, sir. Sir, can you just please share your presentation so we can check?
Is it visible?
Yes, sir. In full screen mode, sir. Yes, sir. Good, sir.
Should I start?
Just a minute, sir. Just a minute. हाँ sir, we will just start in 1 to 2 minutes, sir. Okay?
I hope you can hear me and see the screen.
Yeah, sir. It's visible.
So should I start?
Just 1 minute, sir. Within 1 minute, sir.
Good afternoon. We, on behalf of SYNC Composite Industry National Conference and Exhibition, we welcome you in the second session. And we are going to have a presentation from Dr. Sanjay Palsule, and he is going to have a talk on Palsule process and Palsule parameters for sustainable polymer composites. So Dr. Sanjay Palsule is the associate professor at IIT Roorkee, and he has done wonderful job for the composite, especially for the polymer composites. So now I hand over to you, Palsule sir. So it is over to you. Thank you.
Thank you. Thank you for inviting me, and thank you for so kind introduction. So good afternoon, everyone. The topic has been informed to you is Palsule process and Palsule parameter for sustainable polymer composites. So we are in the age of sustainable development. We have natural fiber reinforced polymer composites because natural fibers are eco-friendly and biodegradable compared to synthetic or inorganic fibers. In case of a natural fiber polymer composite, we have synergistic properties of natural fiber and matrix polymer. The advantage is lightweight and good properties. Because of the lightweight, we have high specific strength and high specific modulus in the composite. There are several advantages: techno-economic advantages, environmental advantages. These composites promote agro-based economy, and economy of India has a significant agricultural economy base. So these are very important for a nation like India with a very big population where one of the main basis of economy is agriculture. Above all, these composites are sustainable. Now, the properties of composites, as we all know, are governed by properties of the polymer, properties, amounts, and aspect ratio of reinforcing natural fiber, fiber matrix interfacial addition in the composite. Now, here is a limitation in natural fiber polymer composite: the fiber matrix interface. Natural fiber are hydrophilic and polar. They easily absorb moisture. Polymer is hydrophobic, non-polar, it does not absorb water. Now this creates a poor fiber matrix adhesion. And this reduces load transfer from matrix to fiber in natural fiber polymer compound. Now, this limits the mechanical properties of natural fiber reinforced polymer composite. The objective is to improve the adhesion with the sole objective of getting a composite with a better and higher property. So there are processes for natural fiber polymer composite. Interestingly, the oldest of this was invented in 1950. Although it was not invented for composite, it was invented by John Mercer for cotton fiber, where a mercerization of cotton fiber is performed. Where a cotton fiber is treated with alkali like sodium hydroxide and it removes all the polarity and the fiber is useful. Now the same concept is used that mercerize a natural fiber and use it as a reinforcement for polymer composite. Now interestingly, John Mercer was self-taught. He was in United Kingdom. By coincidence, I also received my PhD from United Kingdom. First, I was in London, then in Scotland, in Edinburgh, Heriot-Watt University. So there I had heard people expressing high regards for John Mercer. A self-taught person, no formal education, indomitable energy and perseverance. Now, this particular event is, we have academicians and industrialists. So I really admire the indomitable energy and perseverance of industrialists. Although I myself, I have never worked in industry, I have never been in management, but I do understand the indomitable spirit, the energy and perseverance that you all have to contribute to our nation. Compatibilizer process, Parsulia process, combined fiber treatment and compatibilizer process and combined fiber treatment and Parsulia process. So as of now, there are three processes: fiber modification, compatibilizer and Parsulia process. These can be combined to make more combinations, more processes. Natural fiber treatment process, which is basically mercerization, it imparts physical or chemical treatment to natural fiber. I gave you the example of sodium hydroxide. And that improves the fiber matrix adhesion in the composite. The treatment of natural fiber enhances interfacial adhesion between fiber and polymer in the composite. Now, treatments have expanded from mercerization to physical, chemical, and biological treatments. All these have been reviewed, and this is a schematic presentation. Now we have a compatibilizer process. The concept is very simple. We have a fiber, we have a polymer. They are not compatible. So we add an adhesive, a bonding agent. Normally, we have to join two materials, we will add an adhesive. So here, we are using a compatibilizer, which is a coupling agent, and that will improve fiber matrix adhesion in the composite. Compatibilizing agents improve fiber matrix adhesion. The process has been reviewed, but recent reviews are not available. Now, this is a Parsulia process. I am deeply grateful to the global scientific community that they named it in my honor. So I am humbled and I am deeply grateful to all scientists that they have recognized the work that I did in IIT Roorkee in India. Here, it is just the reverse of mercerization. In the mercerization process, the fiber is given a treatment. In Parsulia process, a polymer is given a treatment. It is functionalized. So now the polymer has a functional group. That functional group will react with the OH, with the natural fiber cellulose, hemicellulose, and lignin. So we do not require any compatibilizer. We also do not require any fiber treatment because the treatment is already given to a polymer. Now the functional groups of the functionalized polymer interact with the functional groups of natural fiber. and they gave a fiber matrix addition in the composite. So we first presented this process in 2007, and later on we came to journals from 2013 onwards. So now it's more than 10 years. And these are the several composites that we have made using polyethylene, polypropylene, ethylene propylene rubber, SEBS, ABS. So polyolefin, thermoplastic elastomer, thermoplastic like ABS, and we have also now extended it to polystyrene and styrene acrylonitrile. Now here we have a chemically functionalized polymer. Here is an example of maleic anhydride. Here you have OH of natural fiber. They will react and they will form a monoester and diester. This will form a bond between fiber and polymer. Now this is an esterification reaction, and we have been able to establish that both monoesters and diesters are formed. Now this is the reaction again with polymer and the natural fiber. It will also form hydrogen bonds that we can see here. So first, the previous slide I showed you the ester bonds. This is showing the hydrogen bonds. Both the bonds are actually formed. Now we have also extended to another functionality, which is a glycerol methacrylate functionality. Here the polymer is functionalized with glycerol methacrylate. And again, it is the same reaction with OH. The difference is here an ether is formed, unlike the previous case where an ester is formed. So there is an etherification reaction and also an esterification reaction. In case of GMA, it is etherification reaction. And we demonstrated it with VLDPE and several other polymers. Now we compare our process with other processes. Now here we have example of acrylonitrile butadiene styrene, a fairly high performing polymer. Now we see that these are the values for functionalized ABS. And if we see by Persulet process, we get a strength of approximately 68 megapascal, whereas by other process, we get it maximum of 50. So the maximum value other processes give is 50 megapascal, whereas we are getting almost 68. Here the percentage increase is 55%. Others do not show a significant percentage increase. Similarly, we see for flexural strength, we are getting a value of 115. Others are reporting a value of up to 95. The maximum increment they have shown is 13%. Whereas in Persulet process, we get even up to 50% of increment. Now we see the flexural modulus. It is almost 13 gigapascal compared to others which only get up to 4 gigapascals. So we are receiving 3 times better properties. Now the percentage increase here is 120. Percentage increase here is well above 400. So this is one example of ABS composite where Persulet process composite has significantly higher properties. It is the same polymer, same fiber, only the process is different. Now we come to one of the most utilized polymers is HDPE. Here also we compare. We have this by Persulet process 86, whereas by fiber treatment process it is 25 megapascals. Almost 25, almost 86. For tensile modulus, the value is almost double in Persulet process. Now, if we consider a higher composition with 30% fiber, we are getting 36 megapascals, whereas here they are getting 27 megapascals. Tensile modulus 1.05, here it is 0.99. Now we also consider polypropylene. By Parsulet process, we have 60 megapascals. By other process, it is below 20. In another case, it is 40, whereas in Parsulet process, it is 50. Now we consider tensile modulus. By Parsulet process, it is almost 1.9 compared to 1.1 by any other process. For another composite, it is 3.3 compared to 1.7. So here, Parsulet process has a lower modulus. But in terms of strength, it always shows higher strength. Now let us come to sustainability, because now we also have government norms. We all are moving forward towards a sustainable development. There is awareness for environment, eco-friendly materials, and overall the goal is sustainability. Now, Victor J. Papanak was the first to tackle the issue of sustainable and social design in 1960. So now it is almost 60 years that it has come to where we have reached. R. Buckminster Fuller, he worked for a sustainable planet. And Bertland report was prepared by United Nations. It defines sustainability. Now across the globe, all nations, including India, who are in the United Nations, UNO, they follow this sustainability Bertland report. Sustainability is meeting the need of the present without compromising the ability of future generation to meet their own needs. So we have to consume, we have to live, we have to improve our standard of living. We need better technology, we need better material, better system, in such a way that we leave sufficient for the next generation. We don't end up consuming all the water or polluting all the rivers. We don't end up cutting trees across the world. We need to sustain mountains. We need to sustain rivers. We also need to sustain deserts. They are also a part of ecosystem. So we have forests, mountains, rivers, plants, animals, and we have to sustain ourselves also as human beings. So in addition to the consideration for environment and the finite natural resources that are fast depleting, petrol, diesel, coal, other petro products, they are limited. And we are consuming them at a fast rate. Therefore, we are replacing glass fiber, carbon fiber, nylon fiber by natural fiber and polymer composite. See, production of glass fiber, carbon fiber, nylon fiber, polyester fiber, they are industrial productions and industry cannot be zero pollution. Therefore, we are replacing them with natural fiber. Sustainability considers society and economy of the present and the future generation. So we need to consider sustainability and economy of today and the future generation. Therefore, we emphasize on cradle to cradle rather than the old-fashioned cradle to grave system. Now, this definition is very welcome since 1987, and we all are working for it. Now we come to sustainability of the natural fiber polymer composite. After that, I will come to sustainability of all composites. Natural fibers replace synthetic fibers whose industrial production creates pollution. Abundantly available natural fibers are renewable, biodegradable, and therefore sustainable compared to synthetic fibers, compared to inorganic fibers. Now, natural fiber thermoplastic composites are recyclable. recycling of composites is for their reuse. We also can use the recycled materials to develop these composites. Recycled natural fiber may be used as a reinforcement. For example, we have wooden furniture which is discarded. We can recover wood fiber from that wooden furniture and use it to make a composite. In India, we have a huge amount of bamboo. We use bamboo baskets, bamboo toys, bamboo fiber products, which have a life of 3 to 4 to 5 years. We can recover bamboo fiber from them. We have jute sacks, jute ke bore. We can recover jute fiber from them and use it as a reinforcement. We can also use the recycled polymer as a matrix. Instead of using a fresh polymer, we should try to use a recycled polymer. And we should go for eco-friendlier processes. Now, this is somewhat bit sad because the first process which was invented for this composite was using alkali. And now we say that alkali is unsustainable, chemical treatments are unsustainable. So we have to use new processes that avoid alkali treatment. And that is why the process that I invented got the name Parsule process. Because it has sustainability, we are not using chemicals, we are definitely not using acid, we are not using alkali, so we are highly sustainable. Now, this is a Parsule parameter for sustainable polymer composite. This is not related to natural fiber composite only, it is for all composites. Now, since 2023 and few months ago, 2024, so since last 1.5 years, I am regularly receiving invitations to lecture on Parsule parameter, and I am again thankful to the organizers today in Ahmedabad for inviting me. I am thankful to all the audience that you are expressing interest. Now the Parsule parameter shows that if the recycled composite shows properties comparable with original composite with lower reinforcement, we make a composite with 40% reinforcement, recycle it, the property will reduce. But after recycling, it is as good as a composite with 10% fiber. So original composite of 40% fiber is as good as, after recycling, it is a substitute for original composite of 10% fiber. It can also be a substitute for original polymer or any other original polymer or any other original polymer composite. Thus, the recycled composite is a substitute for that original material. So we have the property of the recycled composite. We have the property of original material. Now we can substitute the original material with a recycled composite. So this is about the Parsule parameter, and good number of persons are now using this parameter to replace original materials with recycled composites. This parameter helps us give values. So this is the overview that I wanted to present. So nice that you have given me almost half an hour. I will be happy to give you some time to ask me questions. So I come to acknowledgements. CECA Asia and Ahmedabad University for inviting me. Indian Institute of Technology, Roorkee, for all the support I received over the years, and my co-workers who have received a PhD and are working, Dr. Priyanka, Dr. Anshu Anjali Singh, Dr. Krishore Biswas, Dr. Dinesh, Dr. Shabdam Pathan, Dr. Piyush Kumar, Harsha Verma, Nisha Tamta. They have already defended their thesis. Hariom Sharan Gupta, Mrudal Pant and Nikhil Chauhan are working with me. Now, these are a good number of references. Few I have shown already. And most of these are related to Parsule process. You can do a Google search, super search with the keyword Parsule process. And I thank you so much. It has been so kind of you to consider me, to invite me. I am deeply thankful to organizers And thanks to all the audience who are present, giving their precious time to attend my lecture. So if you have questions, I am here and I would stop this share.
Thank you, Professor Palsule. May I have some quick questions from the audience, if any? Okay, sir, they are mesmerized with your presentation. You have done such a nice job that instead of creating the fibers, you played with the matrix and could get even better result. So everyone is happy to know your works. Thanks a lot for your time and dedication, sir, for the mankind. Thank you, sir.
Thank you very much.
Thank you. Sir, please.
So if anyone is interested to collaborate, then contact me through email.
Sure, sir. Your voice got a bit distorted, but I can make the point clear that Professor Sanjay mentioned that he will be happy to collaborate with any and everyone present here. Am I right, sir?
Yes, with the industries.
Yeah, yes, sir. Thank you, sir. Thanks a lot.
Thank you very much.
With this, we reach the last presentation of the day, which will be on a very critical topic of the role of composites in hydrogen manufacturing. It will be by Mr. Ketan Pednekar from Scottish Development International. And he probably is available online now. Yeah, there he is.
Hello.
Yes, sir, we can hear you. Hello.
Hello. Can you hear me now? And
Yes,
can you
sir.
see the slides?
Yes, sir, loud and clear. You can start. Welcome, sir. Please.
Yes. Thank you very much. I hope you can see the slides. So let me start my presentation. First of all, let me thank all of you. I mean, the organizers as well as the audience for giving me this opportunity to share my views on role of composites in the hydrogen economy. My name is Ketan Pednekar, and I'm a trade specialist for energy transition for Scottish Development International, based in Mumbai. So this is the agenda for my presentation. I'll first give a brief about Scottish Development International. We'll then talk about why hydrogen. We'll see hydrogen demand projections and opportunities for composites in the transport sector. We will briefly see the research opportunities in this sector and then conclude. First, a bit about Scottish Development International. Scottish Development International is the international arm of Scottish Government's Economic Development Agency. So what we do, we assist Scottish companies to trade overseas and try to attract inward investment into Scotland. Now, Scotland has excellent ecosystem where research institutions and industry work together to solve industry problems and develop innovative solutions. And there are many collaboration opportunities to optimize or to improve composite manufacturing between Indian institutions or industry and Scottish institutions. So if any of you are interested to explore these opportunities, please feel free to reach out to me with specific details of the research area or the problem statement, and I can connect you with the relevant experts. Now, why are we talking about hydrogen? As we all know that climate change is real. According to IPCC special report on global warming, higher temperature thresholds will adversely impact an increasingly larger percentage of life on Earth, with significant regions, ecosystems, and species getting affected. So we are already experiencing rising sea levels, more extreme weather, more frequent wildfires, heat waves, increased droughts, etc. And all these events could be attributed to climate change. World over, the governments have realized this. They are realizing the importance of climate emergency and net zero, and they've set targets for reaching net zero. Scotland is committed to reach net zero by 2045. UK will reach it by 2050. Our own Honorable Prime Minister has set a target of 2070 for India to reach net zero. Now, hydrogen is a versatile energy vector which can be used for achieving net zero in some of the very hard to abate, hard to decarbonize sectors such as steel, cement, industries, and transport. So many governments are giving prominence to hydrogen in their net zero strategy. As you all know, it's the lightest and the most abundant element in the universe. So India also has declared a national hydrogen mission, and growth of hydrogen economy in India will certainly be very rapid if government implements the industry friendly policies and takes bold initiatives. Now, the global hydrogen demand reached around 95 million tons in the year 2022, divided mainly between industry and refining. However, as the world aggressively tries to decarbonize, transport sector, which accounts for almost a quarter of the world's emissions, is an important target area. Sales of battery electric vehicles are growing fast, but the driving range, recharge time, rush for rare earth materials are some of the challenges for growth in this sector. Especially for heavy duty transport with long range travel, batteries are not currently a viable options. Here, hydrogen fuel cell trucks are increasingly becoming more attractive. Besides, world needs all the solutions that make economic sense to reach net zero. So even the passenger vehicles having long range and rapid refueling capability will become attractive to customers in future. So there are many such vehicles already running in California, South Korea, China, and Japan. China sold around 6,000 electric vehicles, FCVs, South Korea around 4,600, California around 3,000, and Japan around 400 FCVs in the year 2023. So, however, as more and more hydrogen projects come online, more and more refueling infrastructure is in place, the sales could really take off. If you see International Energy Association's projections by 2030, hydrogen demand is expected to reach around 150 million tons globally, out of which around 9 to 10 million tons will be used in the transport sector alone. So this will create a huge demand for mobile storage of hydrogen. So considering this demand, 10 to 15 million cars and around 500,000 trucks will be on the road by 2030. And considering automotive type 4 tank requirements for these vehicles, considering 12.4 million passenger cars and 0.5 million trucks will be around 15 to 16 million tanks if you consider 5 kg tank as a standard. Of course, this target is very, very challenging. It is very unlikely to be achieved. Hydrogen Council, which is another global CEO-led initiative that brings together leading companies with a united vision for hydrogen. They have a more realistic outlook, anticipating around 4.5 million FCVs by 2030. So even if you consider this figure, the hydrogen tanks for automotive purposes could be around 5.8 million tanks. So this is really a huge opportunity for Type 4 cylinder manufacturers. Now, European Union is mandating 30% emission reductions by truck OEMs, which will force them to manufacture either electric or FCV trucks. It is likely that around 5% of the trucks manufactured will be FCVs. This means by 2030 in Europe, as much as 50,000 to 20,000 trucks per year will be FCV trucks. Now, Hexagon Purus, a Norwegian company which manufactures this composite cylinders, they estimate that there will be around 630% increase in hydrogen storage tank sales. They expect the revenues from the sales of these tanks to be $1.1 billion in 2025, which will increase to $7 billion by 2030. Now, Toray Industries T700 standard modular carbon fiber has become the benchmark for Type 4 pressure vessels, storing hydrogen gas at a standard pressures of 350 to 700 bar and renewable natural gas at around 250 bar. So now Toray is expecting the demand for carbon fiber or pressure vessels to hit almost around 40,000 tons per year by 2025. And to service this expected demand, they are planning to increase the production capacity to 35,000 tons by year 2025. There is another supplier of carbon fiber, Hyosung, is planning to increase the production capacity to 21,500 by 2025. They're setting up a new plant in southern Vietnam. Now let's talk about the leading manufacturers. Hexagon Purus, they are the battery electric systems and vehicle type 4 pressure vessels and hydrogen systems for vehicles. They are the suppliers with a total capacity to manufacture around 50,000 type 4 cylinders from two sites, one in Westminster, Maryland, and one in Kassel, Germany. Then they have another Hexagon Agility, the company that produces four type 4 carbon fiber composite for renewable natural gas at lower pressure, which includes the systems for truck, bus, and distribution applications. Another player, Faurecia, they first announced the development of hydrogen system for fuel cell vehicles in 2017. They displayed 700 bar type 4 cylinder back in 2018. And after it opening its hydrogen storage R&D center in Bavans, they've announced the contracts with Hyundai, Stellantis, and Renault Hovia to supply those composite cylinders. There's another player, OP Mobility. They manufacture Type 4 tanks and integrated hydrogen systems. It can produce around 150,000 Type 4 cylinders from its Belgium, South Korea, and France facilities. They're planning to add another 60,000 pressure vehicle capacity in Shanghai. Luxfer is one more major gas cylinder supplier from the UK. They are having, the products for 350 bar and for alternative fuels such as CNG and hydrogen. They are exploring 700 bar tanks, but the commercial products are not available at this time. Worthington is one more manufacturer. Its Austria plant is located in Austria, was commissioned in 2021, and they also acquired Portova composite cylinder plant in Poland in 2011. Then Voith is another manufacturer which recently received R134 certification in December 2023 for its carbon 4 tank, 350 cylinder, 700 bar type 4 storage vessel for hydrogen made using a Tau-Preg system. So if we consider Hydrogen Council's figure, the transport sector itself is expected to see a very big growth, and more than 4.5 million fuel cell electric vehicles are expected to be on road by 2030. China, Japan, and Korea, along with Europe, are expected to lead the rollout of these vehicles. The growth in near future is expected in trucks, buses, trains, although passenger vehicles will also see more demand as the refueling infrastructure grows. This is a massive opportunity for composites for hydrogen storage in mobile applications. And as Type 4 tanks are lightweight, they are the preferred option in mobile applications, although they are much more expensive than the conservative ones. Now, French automotive Tier 1 supplier Faurecia and Plastic Omnium forecast production of 2 million hydrogen-powered vehicles per year by 2030. And of these, 1.5 million will be light-duty and passenger vehicles. And Asia, will be the leader in FCV market with 70% of the market share. They claim that 40% of the value of the fuel cell systems is in the hydrogen storage tank itself. And 70% of this 40% cost is for the tanks, and remaining is for the valves and other components. Now, as mentioned earlier, road transport decarbonization is one of the critical aspects of reaching net zero. And today, hydrogen fuel cell buses are in the early stages of commercialization. The selling cost of these vehicles is not yet competitive, and infrastructure issues like lack of hydrogen refueling station network is a major constraint for the widespread commercialization of fuel cell vehicles. Toyota, Hyundai, Honda, they're the leading manufacturers of hydrogen fuel cell vehicles. All of them use Type 4 cylinders. The heavy-duty market also has a considerable potential for hydrogen fuel cell adoption, even though it represents different operating conditions and driving cycles. These vehicles need higher power output, improved durability, and fuel efficiency. Light duty passenger vehicles are used for short and low speed journey, could be managed by electrical batteries. For the long haul heavy vehicles such as trucks and buses, they call for a higher utilization and are likely to require hydrogen. So many city centers now have set timelines for banning diesel power buses. So companies such as MAN, Scania, Hyundai, VDL, they have developed hydrogen fuel cell electric trucks. So fuel cell buses have attracted a lot of attention. Aberdeen, Scotland, they run a fleet of fuel cell buses for public transport. They have been a public demonstration tool and currently source for the data. Many such projects are already implemented using government funding and support. So onboard tanks are typically mounted on the bus roof. Many of the buses use 350 bar storage, thus lowering the compression and tank costs. So Van Hool, Toyota, Hino Motors, Hyundai, Wrightbus, PDL Bus and Coach are some of the companies that manufacture these fuel cell buses. Now, apart from this, the high pressure tube trailers are also vital for hydrogen transportation logistics. So, for widespread rollout of this fuel cell electric vehicles, availability of refueling stations is the key. So, according to a Hydrogen Insights report, there will be around 10,300 hydrogen refueling stations by 2030. And the current infrastructure for transporting hydrogen to the refueling station is limited by the availability of hydrogen pipeline, which is almost non-existent. So it is only available for large-scale industrial units such as refineries or fertilizer units. So here, the tube trailers, which can effectively become virtual pipelines, to transport hydrogen to the refueling stations from the production units within a reasonable distance, say around 160 kilometers. And these tube trailers are now increasingly developed using Type 4 cylinders, as shown in the picture. Now, trains, they are also a very good market for FCVs as they run long distances. And if a rail is to be decarbonized through electrification, costs around 0.97 to 1.3 million per kilometer. According to one 2017 report for Caltrain, it noted that electrification of San Francisco to San Jose commuter line using 22 fuel cell trains, including the construction of hydrogen filling station, would cost around $1.3 billion. However, if you go for a conventional train with overhead contact systems, electrified, so it could cost around $3.1 billion. So there could be a savings of around $1.8 billion if you use hydrogen fuel cell trains. So the infrastructure for buses and trains are also relatively easier to develop as they come back to refill to the depots. So this is a very big advantage compared to the passenger vehicles that need huge refilling infrastructure development. As this market is also picking up fast, and the above picture is taken from Ballard Motive Solutions. It's a Scotland-based company, and they specialize in complete powertrain systems and fuel cell vehicles. And they delivered Scotland's first hydrogen train. Another famous example is Island Train by Alstom. And considering more such requirements globally, this segment is a great market for composite hydrogen storage tanks. The most preferred storage pressure for these trains currently is 350 bar. Now, shipping industry is also responsible for around 940 million tons of carbon dioxide annually, which is at least 2.5% of world's total CO2 emissions. And there is a lot of interest in greening some of these marine vessels. The pic which is shown is a proposed hydrogen-powered ferry in Orkney Islands in Scotland that will be operational soon. And there are very similar projects in Norway as well. Historically, for marine vessels, the focus was more on liquid hydrogen storage. However, increased interest towards compressed gas is seen in recent times. So in marine vessels, there is no one size fits all solution. There's a huge range in architecture, types of vessels, etc. Each solution must be thought out well, considering all the factors. So marine projects are niche projects, good margins, and composites could be ideal solutions for maritime due to harsh environment and corrosion. The applicable power range demands for maritime vessels can be from a few kilowatt to several megawatts. So hydrogen, a low volumetric energy density fuel, may not be ideal for a very long distance travel, being viable for inland or a short sea shipping instead. So hydrogen used for submarine and underwater applications are also being considered. So, but here, along with hydrogen, oxygen also must be stored together. They combine, produce power and water. So global aviation industry is also gearing up to decarbonize. Biofuels and hydrogen play a major role as the batteries become far too heavy for aviation purposes. There are two categories currently employed for hydrogen use in aviation. First involves combustion of hydrogen as a replacement of kerosene in large aeroplanes, while the second employs hydrogen and fuel cell system for propulsion of small aircrafts. Now, Zero Avia, a California-based startup in partnership with UK government's Aerospace Technology Institute program, completed first flight of a commercial-grade six-seater aircraft powered by hydrogen fuel cell. Again, recently, Zero Avia completed highly successful 20-minute flight test of Dornier 228 testbed aircraft at Cotswold Airport on 4th of April this year, confirming the reliable performance of hydrogen electric propulsion system. Now let's talk about the new development and research in type 4 cylinder technology and manufacturing. As you're all aware, wet winding is already an established process, but tape winding has evolved very rapidly in recent times. There are areas for operational efficiency improvements in both the processes. The research is ongoing for improving the operational practices and to improve the production rate. Technology evolution provided by numeric control and automation has really transformed the filament winding. There are degrees of freedom of fiber guidance and manual motions. The introduction of industrial robots have greater control of process parameters as well as improvements in repeatability and manufacturing times. So there is ongoing research to improve production rates, improve problems with kinematic synchronization between the robot and other equipment. Then material selection or development of resins, thermoset matrices have historically dominated market for FRP, fiber reinforced composites. And However, utilization of fiber reinforced thermoplastics over thermoset based composites is gaining momentum. Manufacturing issues limit the widespread employment of thermoplastic resins as they tend to be more complex to process than thermosets, especially higher molecular weight and mild viscosities make their impregnation significantly more difficult. So there is an ongoing research to develop new techniques and new material systems for easily processable thermoplastics. Then recycling, circular economy is also a research area because the focus is on circular economy across the world. Research is ongoing for mechanical, thermal, and chemical recycling processes. The important aspect of hydrogen tank project is selecting a reinforcing overwrap for a liner that provides hoop strength. This is a key quality for high pressure applications that directly affect burst puncture resistance. Carbon fibers are consolidated option due to their elevated specific tensile strength. But again, the cost is a major issue since the significant growth in demand for carbon fiber is expected. Alternative reinforcing fibers such as basalt fibers have been a key focus of R&D studies aiming at tank cost optimization. Then liner is a component whose function is to act as a mechanical barrier between the fluid and structural overwrap. This prevents permeation from several microcracks that are present in the substrate of composite layers. So plastic liners for type 4 cylinders usually employ a thin layer of high density polyethylene or aliphatic amide, and optimizing liner shape is the first step to maximize the tank volume and minimize the total mass. So there are lots of ongoing researches to develop new liner material which has less permeability and which are highly resilient to during tank charging and discharging without causing blistering or collapse. There are several hurdles during the commercialization of hydrogen tanks include minimizing cycle time in filament winding, then safe design, lightweight, low cost, etc. There's a lot of research to optimize the size of composite layer using composite laminate theory, netting analysis, design of dome geometry, then finite element analysis of design, modeling of winding layers, helical winding on geodesic, non-geodesic path, working pressure, cylinder dimensions, etc. So finally, as this field is evolving, there are significant possibilities in testing techniques again, and for certification requirements. So Scotland and the UK can really help you in all these research areas as discussed earlier. We have excellent ecosystem and research equipment as well as the skill sets to design and optimize Type 4 cylinder manufacturing. Their specialized knowledge of materials and modeling capabilities will be helpful in developing new materials and optimizing the cylinder design. We have National Manufacturing Institute of Scotland, which is with the University of Strathclyde. They will help you in developing your own optimal automated and advanced manufacturing processes. Now, University of Bristol recently developed a cryogenic composite cylinders for hydrogen storage. So, working with Scottish and UK-based research institutions can greatly help you in your ambitions for manufacturing Type 4 composite cylinders in India. So, feel free to reach out to me if you're interested to work with any of the above universities or institutions or anything. So, in conclusion, the world over, governments are promoting hydrogen to use to reach net zero targets. Hydrogen storage using Type 4 composites has huge growth potential. The near-term opportunities are with heavy vehicles, railways, maritime. Opportunities will open up for LCVs and passenger vehicles as hydrogen infrastructure is created. And there are many opportunities in research in composite cylinder technology for hydrogen storage. Scottish and UK universities and institutions are well placed to support you in your Type 4 cylinder manufacturing for hydrogen storage in India. I would like to credit these resources for my presentation materials and speaking notes. And thank you very much, everyone, for patiently listening. And thank you, organizers, for giving me this opportunity to speak at the event.
Thank you for such a insightful presentation, Mr. Ketan. May I have any questions from the audience? Okay, thank you, sir. It was an enlightening discussion about the future, and I request one and all, definitely you will join hands in saying that we should attempt to bring that 2070 line to close to whatever we can. So we all should have good efforts toward pulling the strings, and so that we can have it maybe just about 2050 plus few years. Thank you. Thanks for your time, sir. And next time we expect you here at Ahmedabad University for in-person presentation.
Sure, sir. Sure. Thank you very much.
Thank you. Thanks a lot, sir. So, with that, we come to the conclusion of day 2 of this conference. And I thank you all present here and request you to please be sharp on time. Tomorrow morning, 9:30, we meet, wherein we will continue the area of composites in automobile manufacturing. I request all the dignitaries present in the auditorium to please come up the dais for a group picture. Thank you.
Come upstairs. You can join this side.
Yes.
पुढे थांबू ना पुढे अच्छा पुढे आगे जा, पुढे पुढे
Okay.